Okay, so it's a big pleasure to have Noah Smith here. Noah has been coming to the summer school every year. This is the 14th time that he's giving this lecture. We were just discussing with Mario if it was 1 year or 2 years where we were remote. Noah is a professor at the University of Washington and leading a team at AI2. And he's talking about he's giving an introduction on sequence models. So the floor is yours. Thank you.
Thanks, Andre. How is the sound? Too loud, too soft? Good? Okay. Thanks for inviting me back. Thanks to everyone who got up early on a Saturday morning. Every year it kind of switches which day of the week I'm teaching. So Saturday, I guess, is the worst, but um, we'll see people trickle in. This lecture starts with a little bit of shameless advertising. So this is going to be a moderately technical lecture that tries to give you the mathematical and maybe even, I hate this word, but like historical foundations that will help you have a deeper understanding of language models. I think if you want to really appreciate the technology and make contributions to it, then it's helpful to know how we got to where we are and how we learned what we know. And so this lecture will try and give you a window into that. I also have a different talk that's not appropriate for LXMLS, but I try and advertise it a little bit every chance I get. So my sense is that language models are extremely important to our society now, and more people should understand them. And so with a couple of my students, I wrote a book. It's not a book. It's a 30-page document. There was a thought that it could be a book, and it's not a book. It's not that daunting. It has no math. It's called Language Models: A Guide for the Perplexed. If that doesn't make you laugh, it will by the end of the lecture. And there's a talk video on my website that was very nicely produced. I gave the talk at a humanities festival in Chicago last fall, and they made this really nice video, and you can watch me try to take weird questions from a public audience. But basically, this is meant to be a very accessible guide. So if there are people in your life who don't seem to understand what's going on with the technology and you want to give them an introduction that's meant to be friendly and gentle, I recommend that guide. And it's just published on the archive. The link is at the end of my slides, and if you Google it, you'll find it. Okay, so I don't think I need to do a lot of work to motivate why we want to understand language models. I think the place I start when I talk to that broader audience is autocomplete, right? You're writing a text message or an email, and the system offers you some options for what your next word might be. And so this is it. That's the heart of the task. That is what we're trying to do. We're trying to build a predictive system that guesses what the next word is likely to be in a context of the preceding words. That's the simplest version of the language model, and it's been around for half a century, more than that, and intriguing people for all of that time. And what does it mean when you can do that? It's a fascinating question. But there are a couple of other motivations that are worth mentioning. I think these days with apps like ChatGPT, people often very quickly jump to the idea that this is actually not just me writing my email. It's a conversation between me and the system. And so I can ask a question and I get back an answer like in a dialogue. And so if you can predict not just the next word I'm going to say, but the next word that one would say if one were in conversation with me, then that's also language modeling. There's an older sort of tradition of using language models in a range of other applications, like transcribing speech to text or translating from one language to another, or even optical character recognition, where you have an image that has text in it and you want to pull it out and digitize that text. In all of these cases, you can kind of imagine, this is where I'm going to start to introduce a little bit of notation, that the goal is to pick out a word sequence W that is both faithful to the input and also fluent. And so this idea of fluency, that we want, whenever we have a system that's producing text, we want it to look like our language, like English is what language we're using today, Portuguese maybe over dinner. But we want it to be faithful to the input, but we also want it to be just good in the sense that it's language. That second thing, that fluency score, that idea that we can look at any sequence of words and say, how English is this, or how natural is this? That is what language models traditionally provided. So modern language models, where basically the language model is almost the whole system, that's a relatively new idea. But the idea that the language model is a component that gives you fluency scoring is much, much older. That goes back at least to the 70s. Finally, I like to point out that having a language model could also serve us if we're interested in just understanding what language is. Why do other scientists build models? They build models of the universe. They build models of molecules and other natural things because they want to understand them and they want to compare theories. And so it's sometimes been put forward in some corners that if you have a good model of how surprising data is to a model, then you should choose a model that finds the data less surprising. And so language models have also been used to give us a notion of surprise. I'm not going to talk too much about that today, but when we talk about how we evaluate language models, I'm hoping that you'll kind of see that connection and appreciate that is a use case for language models, scholars of language, people who want to understand what language is. All right, we start with probability. Whenever we talk about probability, we have to say what our event space is. It's always going to be discrete today. So if you're like me and your early training was in computer science, this is going to be easy. If you're like Mario and Andre and your early training was in electrical engineering or something, then you're much more comfortable with continuous spaces. You just have to pretend the world is discrete today. We're going to have random variables over those discrete spaces. And a typical statement is something like, we have random variable x, large means random variable. It takes a value little x, which is an element of that set, script x. So get used to this typographical notation. It'll keep coming back. And we say that it takes that value with some probability, which we write p of big X equals little x. Sometimes we'll just write p of little x because it's obvious what the random variable is. And sometimes we have joint probabilities when we have multiple random variables. So we can talk about the probability that big X takes value little x and big Y takes value little y. And we have conditional probabilities. So once we know that random variable big Y has taken value y, we can talk about the distribution over random variable x, given that information. And there's sort of some definitional things. This is always going to be the ratio of the joint probability to the probability of just y taking its value. And there are a few things that are always true based on that definition. We can always break down a joint probability into using the chain rule into a marginal times some conditional probabilities. And hopefully this is just a refresher and you've seen this before. One point that often gets discussed is independence assumptions. Sometimes it's the case that the joint probability of these two events, these two random variables taking their respective values, is equal to the product of the marginals. And what do we call that? Independence. It's today. Tomorrow is there's various Independence Days in July. Canada had one, the US had one, the French. It's not really an Independence Day. The 14th is whatever. Okay. Yeah, I'm confusing. I'm not a historian. Okay. 25th of April. All right. So not Independence. Yeah. All right. So the last thing I want to point out, people sometimes, we talk about all the math and what probabilities are, and we can talk about that all day. We won't. I want to remind you that there should always be in your mind a separation between the true distribution that's always sort of a theoretical construct. Like we believe there's a distribution over sequences of words that constitutes language. That is not identical to the idea of a probability distribution that we're going to estimate or construct by applying an algorithm to some data. There's always a difference between the true thing, which we can never really obtain because we don't have all the information in the universe. We only have the data that we have, and the probability distribution that we estimate. And I'll try and be clear, but most of today we're talking about that estimated probability distribution. Okay, so turning specifically to natural language, I'm going to use script V as the event space for a set of symbols. We often call it the vocabulary. That's why I label it V. So these are discrete symbols. You can think of these depending on your preferences and the language you speak. You can think of them as words whatever words are. You can think of them as characters. If you're a hardcore computer scientist, you can just think of them as the set of bytes. All of these are possible. And so I'll sometimes use large V to mean the size of that vocabulary. So if we're thinking bytes, how many are there? How many distinct bytes are there? 2 to the 8, 128, 128, 256, something like that. Not too many. But typically we build language models with vocabulary sizes in the tens or hundreds of thousands now. And then, but you know, language is not just choosing words. Like I guess you can have single word conversations with people you know really well before you've had coffee. Like breakfast, yes. Coffee, no. We're going to let V star be the infinite set of all possible sequences of symbols from that vocabulary. So now we're talking about sequences. This star comes from, I don't know, it's used in theory of computation often to denote, you know, a sequence of any length from 0 or more. In language modeling, we do one more thing. So we generally tend to assume in most language modeling work that we have a sequence of random variables. X1 is the first word, X2 is the second word, and so on. And this continues up until some n at some finite length takes this special value, which looks like a stop sign, the special end of sequence value. And so I'm going to use V dagger to mean this is the set of sequences of symbols from V, from the vocabulary, with a stop sign always at the end. So it's basically you generate words up until you generate a stop sign and then you stop. Okay, so the language modeling problem, simply put, is you get some training data, you get a sequence, I'll call it bold X, X1 to N, it's N symbols. The last one is, of course, the stop symbol because the sequence is in V dagger. And I'm just going to keep it simple and say you get one sequence. In practice, we often have a collection of them, but that just makes my notation throughout this lecture messier. And it doesn't really conceptually change the way you think about it. So somebody hands you a sequence, and your job in building a language model is to produce a function P, which takes any sequence in VDagger and maps it to real numbers. And the real numbers, you want to interpret them as kind of a measure of fluency or plausibility or Englishness or languageness or something like that, right? Goodness, good language. Does it make sense? Okay, so we're inducing this function from an example, maybe more examples, doesn't really matter for today. Today, the length of that sequence for typical language models, anyone want to venture how big? How big is n today? To build, we actually don't know how big n is for the GPT models. They don't tell us. I built a language model with my team. It was I think 2.4, 2.5 trillion sequences went into the training. Sorry, 2.5 trillion words went into the training. Okay, so here are some questions that we might ask. The first question you should always ask when you start talking about machine learning problems, I think the first thing you should always start with is how are you going to know you succeeded? Don't start building a thing until you know how you're going to evaluate it. Just don't do it, because otherwise you'll end up constructing an evaluation after the fact, and you make yourself vulnerable to, I don't know, some kind of like motivated reasoning and believing that your thing works when you actually have no idea how you would know whether it works. So we'll start by talking about how we evaluate. How do we know we have a good language model? The second question, of course, you want the answer to is how do we build them? And the third one is how do we use them? And I'm going to talk relatively little about how we use them because you already know, and there's more coming later in the series of lectures. I'm only going to take you so far with how we build them. I'm actually going to stop before we get to the transformer. Why? Well, because you can find a million YouTube videos. I think there's a great lecture tomorrow. There's plenty of opportunities to learn about the transformer. Everybody's talking about it. This older stuff, it's much harder to find good information about this and kind of hear the story of how we got to the transformer. So, all right, I'm going to add one more layer. Before I talk about evaluation, I'm going to add a little bit more to the definition of the problem. I'm going to be very clear and say that these language models, they're not just a score. They're probabilistic language models, which really means that P, that map from any sequence to a number, it's going to form a probability distribution. What does that mean? Well, for any sequence that you can come up with in VDagger, vocabulary symbols ending in a stop sign, the score has to be non-negative. And usually in practice, we say it has to be positive. It can't be zero for reasons we'll get to in a little bit. And if you sum up over all possible sequences, remember there's an infinite number of them. V-dagger is infinitely large. Each element is of finite length, but n can be arbitrarily large, so there are infinitely many of them, but that infinite sum has to add up to 1. That's what probability is. Non-negative scores that sum up to 1 in discrete world. Why do we do this? I think there are two main reasons we put this extra constraint. The first is people like probability. They find it intuitive. We use this every day. It's become kind of a casual way to talk. We talk about the odds of something happening or the chance of rain, things like that. And I think interpretability has a certain, attraction. The second is that it gives us access to an extensive set of knowledge developed in other fields, like the maximum likelihood principle, that will give us some guidance about how to build a language model from data. And so the starting point for building language models is very grounded in statistics. The things we do today, I think, are less so, because a lot of engineering knowledge has developed that we don't have great theory for. But the maximum likelihood principle, who's heard of it before? Okay, yeah, see, it's an old friend, right? Let's quickly just say a little bit about maximum likelihood. You have some observations, you have some data. Let's just be very abstract. We're not necessarily talking about language models now. And we define a family of probability distributions that are consistent with what we're willing to assume about the data, whatever that is. But we're very explicit. These are my assumptions. This is the family, the mathematical family of distributions I'm open to considering. And the one I should choose, the maximum likelihood principle says, choose the one from among that family that maximizes the likelihood, the probability of the data you have. That's all. That's all it says. It doesn't give you an algorithm for finding it. It doesn't tell you why. It's just, that's the principle. In practice, what we typically do when we apply maximum likelihood is we say, all right, P is going to be a parametric family. That is, it's a family of models parameterized by some free values theta. And so what I'm doing when I'm choosing in that family is I'm choosing the values of theta. I'm picking numerical values for each of these parameters. So for example, let's pick the simplest one. This is the first probability distribution you learn about when you learn discrete probability. We have a sequence of n observed coin flips drawn from heads or tails. So this is kind of like a language model, except the vocabulary is just heads and tails, and we're not worrying about the stop symbol. So we assume, let's be clear about our assumptions, we assume that a single coin gets flipped repeatedly. Do people remember what coins are? Okay. You flip the coin over and over. And so, in our universe, we tend to believe that when you flip a coin multiple times, it has no memory of the previous flips. If you believe otherwise, great. But, and each time the distribution over what's going to happen is the same. So we can say there's a single parameter here, which is the probability the coin will come up heads. Call that theta. It's just a single real value. And you can do a little bit of algebra. You can write down for our sequence of n coin flips the total probability of that sequence under this assumption as a function of theta. So I'm going to multiply in theta once for every heads. I'm going to multiply 1 minus theta in once for every tails. And I'm not going to go through the derivation. It involves a couple tricks. But basically, you can prove that the theta value that will maximize the likelihood is equal to counting up the number of heads that you have and dividing it by n. And this is, I feel like this is something, yes, you can prove it mathematically, but it's also something that people intuitively believe is true. Probably not because they were shown a proof, but because they thought about it. And, it's sort of like the more heads you see, the higher the probability should be. Do you share this as an intuition? Yes, some people do. Okay. Okay, so speaking very generally, whenever you have probabilistic models that are based on sort of like discrete events, and you're just sort of assigning probability to the different events, this is called a binomial or two multinomial for more than that model. And what you end up doing to do maximum likelihood estimation, maximum likelihood estimation just ends up being a fancy way of saying count up what you saw and normalize it so it sums up to 1. And so this is familiar and intuitive, and It's how language models got started. Okay, but back to the first question. So now we've scoped ourselves to probabilistic language models, and I've hinted that there are probably going to be parameter estimates involved in building a language model. Let's talk about how we evaluate. Again, I think this is the question you should always start with before you build things in machine learning. You should understand how you're going to know whether you succeeded. So my claim is that we should prefer a language model that's less surprised by new data, that was not used to build it. That's really important. We'll come back to it. So I like to think, if we have some assumptions about where our data came from, maybe we want to evaluate our model on similar data that wasn't used to build the model. Maybe we're actually interested in how well the model will do in new situations that are somewhat different from the data that we drew, the data we were able to get for training. Both of these are interesting. People use the term in distribution or out of distribution. I think that's a little vague for my taste. I like to focus on what it is about those distributions that's important to the analysis. But the bottom line is we're going to need some data that we did not use for training. So I'm going to put a little bar over things that are in this special test set. It's like this comes specially stamped and approved. It was not used during training. And so if we have a test data set, call it X bar, let's say it's n bar words length long, what we're going to do to evaluate the language model is simply query the language model and say, how probable is this test data? Here's the test. Tell me, how surprised are you? How likely is this? What number would you put on this? And that value will be very small because remember, V dagger is infinitely large, which means the probability pi is being divided up among a very large set of possible sequences. So for any one particular sequence, this will be a tiny number. And it will decrease as you get longer and longer sequences. Eventually, you're going to start seeing a decrease in probability. It just has to be true because we have infinitely many sequences, and we have to divide up that one. It sums up to one. So we're gonna put that probability that we get out of the language model through a transformation that is probably, if it's the first time you're seeing it, you're going to go, why? Why would you do this? You take 1 over the probability, and then you take the n bar root of that value. This is usually not intuitive to people. It certainly wasn't intuitive to me. Let me write it in a slightly different way, and I think it becomes slightly more intuitive. So let's start at the right edge. We take the probability, and we're going to take its log. So what does that do? It takes a tiny, tiny number. If that number is between 0 and 1, it will map to a value between -infinity and 0. Negative numbers are weird. I'm a computer scientist. I don't like negative numbers. So I'm just going to negate that. So now a really big number, negative log of the probability, a big number is bad. A big number means the model was very surprised. The next thing I'm going to do is I'm going to divide that by the length of the data, n bar, so it becomes a per word measure. Okay, so at this point, you can think of it as how many bits on average did the model assign to each word? How much information would the model be using, how many in bits, to encode this sequence on average per word? And then I exponentiate it because well, that's just what we do for Perplexity. It's to undo the work of the log. So what you're going to get from Perplexity is a positive number, and lower is better. And so you can think of it, as kind of a score. And I like to think about the special extreme cases. So imagine that your friend built a language model and they did a really good job. They did such a good job that they put all the probability on exactly the test sequence that you presented to them. You should be suspicious of this friend. How did they know, right? It's like a student who does too well on the exam. But if they did this, perplexity would be 1. That's the minimal possible value. And you should see that by plugging in a 1 into the formula. 1 over 1 is 1. The nth root of 1 is 1. If, on the other hand, your friend did a really bad job of building a language model, your friend didn't consider all possibilities, your friend, I don't know, didn't understand the mathematics of the evaluation, and they put 0 probability on X bar. This is probably what most of us would do the first time we built a language model if they hadn't seen this lecture. Perplexity will be infinite. The model will be infinitely perplexed. So it's important to make sure if we're going to evaluate with Perplexity, that kind of sets us up to always remember in the back of your mind, anytime I build a language model, I have to make sure that I assign strictly positive probability to every word in every context, every sequence of words. There is a way we could talk about this a little more and try to illustrate it with examples, but we don't have time. You can kind of think of Perplexity as like the effective vocabulary size. It's like on average, when the model's making predictions, how many words is it able to narrow down to before it makes a guess? So 1 means it always knows perfectly well what the next word is, at least with respect to this test set. A couple warnings. Perplexity is really cool. It's amazing when you have a problem that has an intrinsic evaluation that doesn't require special data. You just have to decide what your test set is and make sure it's not in the training data. But there are some things you have to remember. First, you can't directly compare perplexity values of models that use different vocabularies. If you build a byte-based model and I build one based on some other notion of what words are, the numbers will be apples and oranges. It won't make any sense to compare them. There are some tricks that people use to try and come up with maybe possibly fair ways to do this. And we won't talk about it today, but you can easily find discussions of that in the literature. People often fixate on the specific values of perplexity. And these days, the numbers are in like the single digits sometimes, depending on the vocabulary and the language and so on. I'm not going to talk about specific perplexity numbers because 1, I don't want to change these slides every year. Language models just get better and better, and that's not really important for today's lecture. But also because I don't want you to think perplexity is really the end goal. Perplexity is a really beautiful, useful tool. It's an intrinsic measure of the model quality or the model's fit to some new data, but it doesn't tell you what data the model was trained on, when you expect it to work or not work, and it doesn't tell you how well that model will work in a practical setting with real users. So I think for today's purposes, I want you to understand the models, how we got at them, how we developed them, what they're supposed to do in terms of how they make predictions. I don't think it's important to remember specific trained test sets and know like this is the value we're getting on this particular benchmark this year. They're changing. In fact, we just put out a new perplexity benchmark called Paloma, which takes samples of data. I think it's 580 or something like that, different test sets to encourage people to think broadly about how perplexity values are affected when you change the design of your model across different kinds of data. And some of the data is like coming from different dialects of English or technical domains and so on. Okay, quick aside, just sort of a reflection moment. You can plug in any data you want when you calculate perplexity. You can plug in the training data if you want. Nobody's stopping you. If we did that, what do you think would happen? Suppose we built a language model using reasonably good techniques on some training data, and then we said, hey, model, what's the perplexity of the training data? Would it be low? Would it be high? How do you think it would compare with the perplexity of test data? Probably lower. The model should probably be unsurprised by the data that was used to train it, right? That's one of the reasons we don't usually report training data perplexity, right? We don't think of that as a particularly interesting measure. It's like testing a student on the examples that you showed them in the lecture before. Maybe it's good for their ego, but it doesn't actually help, show whether the model learned anything. Okay, this is one of the things that I think people really don't talk about often enough, and I could spend probably an hour or two just talking about it, but I will not. I will only spend a couple of slides. How do we design the vocabulary? Where does it come from? People often treat language model vocabularies as if they were handed to us by God. Like, this is the vocabulary that was used for these other models, and I'm not going to question where it came from. But I think it's really important to recognize that this is a very critical design decision that will affect everything that happens with your model. So how do we design the vocabulary? Here's the most naive thing that I've been teaching NLP in the classroom for almost 20 years. And so I will summarize to you what undergraduates in universities in the United States will often say. Oh, you just take the text and you call a Python function that splits it on white space. And then you've got tokens, kind of like you have tokens when you build a compiler for a programming language. And you treat white space as the delimiter, and anything that's a token, you just call it a vocabulary element. The word for a vocabulary element is type, distinct from a token is an instance of the word in the text. The type is now we've promoted it and it has a special place in the vocabulary. It's an element of script V. So this is this is not crazy, except if you actually go and look at text, you'll notice that there are a lot of words. First, there are a lot of words, even just in English, which is a pretty simplistic language when it comes to word formation. English doesn't have a lot of like extra suffixes and endings and things that change inside the word, like languages some people here might speak. It has some variation with capitalization, like sometimes you'll see a word with the first letter capitalized or the whole thing capitalized, and those will end up being different words with this naive method. Sometimes you'll have like a comma at the end or parentheses around the word or something, or like missing a parenthesis. Look at that. I misspelled the word misspelling. And also, but here's the thing, right? If you have a broader view of the world, who here speaks a language that doesn't use white space? Okay, at least one person. There are languages that don't use white space, so this method makes no sense. For those, this is a naive solution. If your data set's not too big, you probably won't experience too many problems. But my take on this is you will probably have too large a vocabulary if you do this. You will probably split apart words that really should be treated the same way. A safe solution at the other extreme, which is not insane, I think, is to build models based on bytes. Just say, all text ultimately is encoded as a file, and I can break that file down into a sequence of bytes on a modern computer, and it doesn't matter where words are or anything. Just call it a sequence of bytes and call it a day. And now my vocabulary size is 2 to the 8th. This is appealing. Some people here are thinking, what could possibly go wrong with this? And there may come a time when this is what we do. It's really not crazy. Technically, it's a very nice solution. But the problem is that you're going to have very long sequences, right? You're not going to get any benefit from recognizing that this sequence of bytes, which repeats over and over and over again, for example, in English, the sequence of bytes that spells the word the, T-H-E, it might be nice if we could get away with using a single integer for that rather than a sequence of 3. Everything is just going to be much longer by a significant factor if we do things at the byte level. So basically, that particular trade-off of having a very small vocabulary but everything being much longer sequences, I would say there may come a time when this is a good solution. There are definitely people who want to do it this way and have explored how to make it practical, but it's not practical yet. This is not the way anybody does it. So keep this in mind. In 5 years, 10 years, 6 months, I don't know, byte level models might take over the world, and you'll be like, oh yeah, I heard about that in Noah's lecture. It's not insane. He said it was okay. I'm not going to panic. Here's what we do today. All right, and I'm giving you a very short version. If this were a longer class, we could take the whole afternoon and try to re-implement it. It's an interesting algorithm. You'd start with data. Okay, data is always great. You take a sample of data. It might be your training set or a subsample of your training set. And you basically apply a classical rule learning method that starts from bytes or characters and says bytes, my vocabulary is bytes. And then iteratively finds frequent sequences, like the most frequent sequence of 2 bytes that occurs as a pattern. And I'm just going to merge that into a single token, and add that as a type to my vocabulary everywhere it occurs. And I just keep doing that iteratively. So I build bigger and bigger sequences until I reach the vocabulary size that I'm willing to deal with. So I just set the max vocabulary size based on my computational budget. And I call it a day. And there are variants of this. There's different assumptions that you make. Typically, in NLP, people will assume that they're not going to do merges across white space, for example. The devil's in the details. I haven't given you enough to re-implement this, but the keyword, if you want to go look it up, it's byte pair encoding. And it's something like byte pair encoding is used almost universally to build language models. If you don't run this algorithm, then chances are you borrowed a vocabulary from somebody who did. And so I would say that, just sort of notice this approach is safe in the sense that you will always be able to tokenize text into things that are in your vocabulary. If you see crazy new words that don't look anything like your training data, at least you'll be able to look at it as a byte level sequence. So you always have that fallback. Okay, so here's our universe. We're focusing on probabilistic language models with a fixed finite vocabulary, and we're assuming that, and the only things we worry about are the things in that sequences of symbols in that vocabulary, and we've constructed it in a safe way, so any sequence of bytes that we see we'll be able to deal with. We're starting from the maximum likelihood principle for training the model, for constructing the model. We have training data, x1 through x big N, and we evaluate perplexity on some separate test data, which we have convinced ourselves is not in the training data. In other words, the training data is not contaminated with the test data. We're going to use x bar to denote the test data and bar n to denote the length of that data. Typically, n is really big now, like trillions. In years past, maybe 5 to 10 years before I started teaching at the summer school, n was in the millions. So we've seen, I think it's fair, I don't use the term exponential growth lightly, but I think it's fair to say we've seen exponential growth in the amount of data that we use to train language models, and that, as we'll see, has been transformative. Okay, but we want to start at the very beginning. We want to imagine how we're building language models, and we want to start, I like to, put myself into the mind of someone who's never thought about this before, and start from the maximum likelihood principle, which tells us in discrete worlds, the probability should be proportional to the number of times we see a thing. So let's start there. Let's imagine that we're going to assign to a sequence X a probability that is proportional to the number of times we saw it before, that is in the training data. Sound good? I mean, it should sound good. It's aligned with the maximum likelihood principle. But here's the problem. We already said X bar couldn't be in the training data by design. The test data should be separate. And so we expect that, let's assume perplexity is the game. This is going to fail pretty badly if X bar is not in the training data. We're going to get infinite perplexity almost by design. The issue doesn't go away, by the way, if we assume the training data was multiple sequences, right? If I only have one training sequence, then the probability is 1 on the training data and 0 on every other possible sequence. If I have multiple sequences, I'm still going to have a positive value for anything that was in the training data and a 0 for anything that wasn't. So we don't do that. All right. We can get through that very quickly. That doesn't work. That's a very classic case of overfitting your training data, right? Putting probability 1 on anything that is your training data and 0 on anything that isn't. Not useful. So what we do, the typical starting point, not universal anymore, but for today's purposes, this is where we start. We remember that this is a sequence of discrete random variables, x1 up through whatever point at which we generate a stop symbol, so variable length, and we use the chain rule. So the chain rule says you can order your random variables any way you like, and you can talk about the marginal probability of the first one, and then the conditional probability of each one after that on the ones that came before in the ordering. And so a very natural ordering is to start at the beginning of the sequence and say that the first word was generated first, the second word was generated second, and so on. I'm always going to gesture to your left when I talk about the beginning, and your right when I talk about the end, because I speak a language that's typically written left to right. But if you prefer it the other way, you can think of it the other way. It doesn't matter. We're not really talking about text on the page. We're thinking about beginnings and endings. So the beginning will be over here by today's conventions. So we generate the first word. Conditioned on that, we generate the second word. Conditioned on that, we generate the third. We have lost nothing by making this assumption. This isn't an assumption. This is just applying the chain rule. Okay, I want to be very clear about that. You may lose something in setting things up this way through the algorithms that you're eventually going to use when you apply your language model. But setting up the estimation problem by writing down the joint probability of all the words in this way shouldn't lose you anything. And so the game, when you set it up this way, is to say, well, now instead of predicting whole sequences of words or scoring whole sequences, I break it down into this product of single word probabilities conditioned on the words that came before. And so if I want to do this well, what I have to do is figure out how to summarize that very detailed information on the right-hand side of the conditional bar to make good predictions about what comes next. There are an infinite number of possible things that could happen in the history. I probably cannot remember for each one a distinctive distribution over what can come next. I won't see every history in my training data. So somehow I have to generalize from the histories I have seen when I saw my training data to make predictions in the future. Okay, let's do the absolute simplest thing we could do. Ignore it. Ignore it. All histories are the same. It doesn't matter what happened before. Let's define a language model by saying the history is always empty. I have no recollection of what happened yesterday, officer. I just generate the next word that comes into my mind, and I'm always. One way to think about this is I like a physical metaphor. I have a huge die, like at a casino, and it doesn't have 6 sides. It has V sides, and on each side is written one of the words in my vocabulary. And for every word, I just roll the die and see what comes up. And that's my word. And then to generate the next word, I do it again, and I just keep doing this until I get a stop symbol, and then I stop. So theta, the parameters of this model are just the probabilities of the words, the marginal probability of any word being drawn on any draw. And so you can set this up. This is called the Unigram assumption. We call this the Unigram model. It's usually the first model you see in a classroom. I am a little bit of a contrarian, so I start with that really stupid model that just memorizes the training data so that you've seen it. So this is our second model. And it's really easy to work with. It's very, you should have the intuition that if I have training data, all I have to do to estimate the parameters is to count the number of times I see each word in the training data, divide by the size of the training data, and I am done. Very fast training algorithm, very easy. Have you seen this before? Would you have thought of this if I had stopped the lecture 3 minutes ago? I hope you would. This feels like child's play. This is like I want to build a distribution over sequences of things that come out of a vocabulary. What's the dead simplest thing I could do? I could assume that every element in the sequence has nothing to do with the others. Okay, great starting point. Very easy, computationally cheap. I only have to scan over the training data and remember how many times I saw every possible word. So just to give a very clear example, we have a sentence: presidents tell lies, period, followed by an implied stop symbol. The probability of the sequence is the probability that random variable takes the value presidents times the probability that the random variable takes the value tell times lies times period times the stop symbol, written in Unigram notation, theta for each of those things. If we use the maximum likelihood estimate for theta, this is basically multiply in the count of each of the words that you see, divide by n for every one of those, and you've got your probability. Okay, so pause. Imagine that I was building a Unigram model and I had no data. So I didn't really have a good way to estimate the thetas. So I just said, I'm lazy. I'm just going to set theta to be 1 over v. I'm just going to make it a uniform distribution over the vocabulary. This is like a Unigram model, but for extremely lazy people, or I don't know, for people who don't believe in data. If I built this, why not? Today we're in the space of ideas, so it's free. Actually, this one really is free, right? I don't have to do any work. I just built the model. I just set all the parameters to 1 over v. What will the perplexity of this model be? Do you remember the formula? It's not the square root of v, it's v, but you're very close. Notationally, you're close anyway. It's just v, right? 1 over v is going to give you v, and then you take, but it got multiplied in once for every word, which is n, and then or n bar, and then you take the n bar root, and so the exponent goes away. The perplexity is the vocabulary size. So I love this as a point, in understanding perplexity. This is as bad as it should ever get, right? This is the laziest model in the world. If you ever build a language model and you go check the perplexity and it's larger than the vocabulary size, you've done something wrong. You probably have a bug, right? Or you're not looking at your data properly. Something is off. It probably has to do with your implementation of Perplexity because logs are complicated, or maybe it has to do with an off by one error or the way you encoded your vocabulary. I don't know. There's a dozen things it could be, but you definitely did something wrong because if you're going to do the effort of applying machine learning to a problem, you'd better be able to beat something that's that stupid. Okay, so this is like a good mental check. Perplexity should always be smaller, ideally much smaller than the vocabulary size. That's why I like to remind you, think of Perplexity as like the effective vocabulary size. If it's worse than doing this, you've done something wrong. There's the math. Sorry, I should have remembered that I wrote it in there. So remember that the probability of the sequence has to multiply in 1 over v once for every word, and then it undoes itself. Okay, Unigram models, the cheapest, simplest language model. They're very easy to understand. You probably would have thought of them if I had paused and let you think how you would solve the problem the simplest way. They're very cheap. They actually there was a period of time where people were building simple search engines based on this idea. I think that's not how Google works now, but it's a part of the story. There are a couple of drawbacks. The first, I always have to reiterate, the vocabulary assumption, the fact that the way we built our vocabulary is probably not a perfect reflection of the way language works. That's always going to be with us. That's not going away today, but I'll keep bringing it up so that you don't forget. One way to think about Unigram language models is they're making this assumption. The Unigram assumption is like saying that words are drawn out of a bag, right? I have a bag of words that are all in there with different frequencies, and I just kind of keep drawing a word out with replacement without any memory of what came before. This is not accurate. This is just not the way language looks. The sequence the, which is not really English. It could happen, plausibly, but it's going to be much higher than a much more plausible sentence on a hot day today, like "I want ice cream." Right. So anything you can think of that is legitimately English, you can think of something else that just uses more frequent words more frequently that will have higher probability. So there's something fundamentally broken. You should not feel like we've accomplished anything with this model in terms of describing how language works. Okay, so we go very quickly to let's make a slightly weaker assumption and say that the next word depends on the history, but only the most recent history, only a small number of previous words, a fixed small number of previous words. So let's call that number little n. And we're going to call this the n-gram assumption, and we're going to call these n-gram models. Have you heard of n-gram models? Awesome. Okay, I don't have to belabor this. When we make an n minus first order Markov assumption, we have an n-gram model. So the n-gram refers to the history of n minus 1 words plus the word we're predicting. If we set n equal 1, therefore, we have a 0th order Markov assumption. We have the Unigram model. There was a period of time when this will date me, when I started in the field, when speech recognition systems were using trigram models, that is a history of 2 words. Later, by the time I got my PhD, it was very common to use 5 grams. And it kind of kept, you can probably find papers with 7 grams, and it probably kept going. But essentially what this means is that your parameters are now conditional, they're estimates of the conditional probability of a word in the vocabulary given the sequence of n minus 1 words that came before. So if you wanted to estimate this very completely and lay down everything you were doing when you built an n-gram model, how many parameters do you have? How many conditional probabilities are you gonna write down in a table that stores all possible things that could have happened in the history and all possible things that come next? Keep thinking about it. We'll come back. Here's maybe an easier question. If I'm trying to write down how I'm estimating one of those probabilities, so the probability of word v given a history h, where h is some sequence of n minus 1 words, how do I write this down? What's the maximum likelihood estimate going to be? What am I going to store in that table? I'll give you a hint. Go back to the maximum likelihood principle. Trust your instinct. How do we do maximum likelihood with discrete events? So it's going to have something to do with the count of the word and the history together. That's definitely part of it. What else do we have to do? We have to make sure the probability estimate sums up to 1 across all possible words. So we have to normalize it. So here's the math. Starting from the definition of conditional probability and plugging in the estimates for the two things in the ratio. So we have the probability of the word V with the history divided by just the probability of the history. And so you're actually going to have to count both of those things. And the n's in the denominator will cancel out. So you're taking the ratio of the number of times I saw this history with the word divided by the number of times I saw the history. A common mistake is that people forget it's a conditional probability, and then they only estimate this part. They take they divide by n the number of times I saw some word with some history, and then they make their perplexity far worse than they need to be. So it's sort of like, remember, conditional probabilities require counting two things. But that's it. That's essentially it. There are going to be problems when you're dealing with histories you never saw in the training data, which is almost surely going to happen. You're also probably not going to see every history that you do see with every word. So dealing with zeros, that's an issue. I'm not going to talk about it right now. Okay, so counting is how we're going to get those probabilities. I've hinted that there are going to be a lot of them to estimate, but we haven't quite said how many. Suppose I give you a sequence of words and I say we need to get the probability of the sequence of words. Maybe we're doing a perplexity evaluation. How would you calculate its n-gram probability? What are you going to do? We've already built the model. We've stored everything we need to store. We have access to the parameters. What are we going to do? This is a simple question. Don't overthink it. The combination of you take every n-gram that you see. You're not looking at the training data. You're looking at the sequence that I give you, and you're looking at the parameters. There's a verb I want to hear. Every n-gram, I'm going to go and I'm going to look up the probability of the nth word given the other n-1. I'm now going to get one of these for every word in the sequence. What am I going to do with those values? Multiply, that's the word I wanted. I have to multiply them together, right? It's just like the Unigram model, presidents tell lies, period, stop. It's just like that, except now it's presidents given empty history, tell given history up to presidents, and so on. Each word conditioned on its history, I'm always multiplying in one thing for each word. And those numbers might be tiny, so I often do this in the log domain. I often take the logs of them and add them up and then exponentiate if I need to. But keep in mind, for every word and every history, I have to go look up the probability. So I'm going to want a data structure that's very efficient for that lookup. And I think that's kind of an important engineering consideration. If you were building a language model like this, you want to think very carefully about how you're going to make random access of n-gram probability lookups as fast as you can. I'm not going to tell you how to do it. There are great papers on this from 10, 15 years ago. And great code bases, actually. People still use KenLM. Has anyone heard of KenLM? Yeah, still around. Yep. Okay, so here's the thing. I sort of said you can pick a finite history length, and I told you that historically it kind of got longer. But I want you to think a little bit about how we choose that history length. So the first thing to say is that as n gets larger, you have more history word combinations you need to parameterize. And I'll now answer my question from before. The number of parameters, the number of things in that table, at least in some abstract sense, needs to be v to the n. That's how many n-grams there are. Number of words in the vocabulary, and each one you have n choices per word. When I say parameter, I want to be clear about how to think about parameters, because this is a very important concept. Can anybody tell me what is a parameter? We throw this word around all the time in machine learning. What's a parameter? You can think of it as a random variable if you're Bayesian. We don't need to be Bayesian. We don't need to do that today. You can think of it that way. It's sometimes helpful. Andre is going to have a heart attack if I say that again. Here's how I think about a parameter. I imagine that I like physical metaphors, simple things, mechanical things. I'm building some kind of machine, and the machine can be customized. And so every customization choice I can make has a knob, and I can turn that knob, and that changes the behavior of the machine. And a parameter is just a knob on the machine. Okay, so when I'm building an n-gram model, I have v to the n knobs. In actual fact, some of those knobs I don't explicitly set, because when I count things, there's a whole lot of events I never see. A lot of n-grams are never going to be seen in the training data, and I can implicitly assume under maximum likelihood that their values are 0. So it's sort of like it comes from the factory and everything's set to 0. And whenever I see stuff, I'm changing parameters based on how many times I see n-grams. That's a way to think about how you build an n-gram model. So I like to think of parameters as knobs. All right, they will come back. There will be more and more parameters as the day goes on. Okay, so most of the n-grams will never be observed, and so they would have 0 probability. And this is if you ever hear the term data sparsity, this is literally what it means. If you think of all the knob settings, all the counts that I'm estimating when I'm building my n-gram model, everything starts at 0. Most things are just going to stay at 0 the whole time. It's a big sparse tensor of counts because most things don't happen. In order to get good estimates, you kind of do want to see everything happen. And so there's a tension here. As you build a model with a larger and larger n, with longer and longer histories, there are exponentially more of these events that you're not seeing. And so the expectation is that you will need more and more data if you want to generalize well. Most things won't happen. The things that matter, the more data you have, the more likely you are to see them. This is, if you're familiar with the idea of a bias-variance trade-off, this is, I think, one of the most simple, elegant illustrations of that idea. When you have a very small n, like a Unigram model, you have a very biased model that makes extremely strong and wrong assumptions about the data. But you're not as worried about this sparsity problem. You probably will see most of the words, and there are simple things you can do to correct the probabilities so that you always get a non-zero value. As n gets longer, you are decreasing the bias. Your model is now much more flexible and can represent more interesting distributions because it pays more attention to the history. But you need more data to get good estimates of all those events, and your model is more likely going. There's more variance in the estimates that you're going to get depending on the data. All right, so this is I cooked this up because now that we have a few things under our belt, we can talk about language modeling research from a very high level, in a very high level way. And this is I would argue that this is essentially this sort of diagram, which we'll walk through, hasn't really changed fundamentally in the entire history of language modeling. Like, the world's changing fast. The technology in our field is changing very fast. I like to find things that I don't think are going to change and hold on to them as long as I can, because I'm lazy. And you should be too. You should be too, right? You should look for underlying principles that don't change. It's the only way to preserve your sanity in a fast-changing world. So what are some things we can hold on to? Well, language models haven't gone anywhere. They've been around longer than me. They've been around longer than everybody in this room. Let's think about ways we can make language models better. And I'm going to claim that most of the things people can do to make language models work better involve 3 different kinds of moves. So the first one is the one we were just talking about. We can increase the model capacity, give the model more flexibility. In the n-gram language modeling world, this means make n larger. Allow it to represent distributions it could not have represented with a smaller n by giving it an order magnitude more parameters. Okay, so that's the first thing that almost always happens when we increase model capacity, is we have more parameters to estimate. That means probably going to be more expensive to train the model and to store it. Increased computational cost is going to be maybe the downside. But the good news is that if we increase the model capacity, we will probably do a better job of fitting the training data, which that's what maximum likelihood estimation tells us to do, is to come up with the best the model that gives us the highest probability on the training data. So that's good news. That might, maybe, if we're lucky, give us better test set perplexity. If we didn't overfit, if we generalize well, then maybe we've done a good job of getting better test perplexity, and maybe that means better performance in application. Again, perplexity is sort of a proxy. If I fit data better that I haven't seen before, I expect better performance when I use the model in applications. Okay, so that's sort of, and maybe increasing the model capacity will give me better generalization. That's always an empirical question. You always have to go see. Sometimes you made worse assumptions. You built a more powerful model, but it actually didn't do a better job of generalizing. The other two things that you can do to make your model better, we'll start with the easy one, which is to change your training data. And typically the story has been more. Just get more data. I remember going to talks 20 years ago where people said things like, stop trying to be clever about how to build your model and just be clever about thinking about how you can get more data. Today, I would modify that very slightly and say sometimes it's not about more data, it's about better curated data, better selected data, data that's more appropriate for what you want to do. If you have more data, it will cost you more. You will have increased computational costs. You should get better generalization. That is generally what we expect. More data should lead to a model that generalizes better. If we have better generalization, then all those, those evaluations that we care about, the benchmarks of this stuff up here, perplexity, performance and applications, they should get better. Not always. We have to check. Maybe if we have better generalization, we have a model that advances our knowledge about language. That's a lofty goal. Don't know. Have to check. The last thing you can do to improve language models is to understand better what you're trying to model and bias your model in a smarter way. In other words, make better assumptions, not necessarily weaker ones, just better assumptions that are more in line with whatever it is we're trying to model. Okay, this shouldn't be a controversial statement. If you build a model that makes better assumptions that are more in line with reality, the model should generalize better. The Copernican model of the planets going around the sun turned out to be a better model. Okay, really quick. Improving inductive bias in Ngram world, really, it boiled down to a branch of research that was very heavily studied for a few decades, where it basically was, how do you deal with those zeros? The zeros are a problem. They're a problem for perplexity. They're a problem for, you want your model to be able to assign fluency scores to anything. Anything could happen. You need to make sure the probability sums to 1 for every Ngram distribution over, and by extension over the whole set of sequences. But you also don't want zeros. So what do? The simplest thing you can do is you add some fixed value to every count, including the counts that were 0. So get that factory model and set the defaults not to 0, but to 1 or to 0.5 or something like that. That's sort of the starting point. And then there was a whole sort of zoo of methods. This problem is called smoothing your language model, smoothing out the probabilities. There was a method invented in the late 90s called modified Kneser-Nye smoothing. There was a nice tech report in 98 that kind of showed this was the best thing, and it stayed the best thing for a long time. By 10 years later, people were very excited about ways of evaluating language models in applications like machine translation, and they didn't care as much about perplexity. They were also excited about distributed computing and building language models across huge numbers of machines without necessarily storing the whole model in one place. And so they came up with simple solutions that didn't respect that sum to 1 rule. There was one called stupid backoff. The name is just kind of memorable. It didn't really technically form a proper probability distribution, but they weren't really evaluating it on perplexity. They were only using it as a fluency score effectively in translation systems. And so it was fine. So you can find lots of solutions to this. We don't talk about smoothing much anymore. And that follows from the kinds of models we build today. But I like to bring these things up, these like historical relics, so that if you hear an old person use these terms like smoothing or Ngram, it's not surprising, and you can think about how it maps onto modern models. I also want to point it out because there are sort of like descendants of these choices you have to make in modern language modeling. So again, my definition of parameter is very physical. My definition of hyperparameter is a little bit more hand wavy. After you've decided, I'm going to build an n-gram model and I'm going to smooth it, you have some extra decisions you have to make about how you execute this, how you build your model. And these are going to affect perplexity and task performance and the quality of your model and everything you might measure about it. These decisions matter. And the decisions include things like what's the length of the history in my n-gram model, or if I use smoothing, what are the parameters of the smoothing model? We call them hyperparameters. Hyperparameters are super annoying. They are super annoying. You can't avoid them. They're choices you are forced to make. And they're usually not interesting choices. It's not like there's a constant in the universe that tells you what lambda should be in Lidstone smoothing. And like, some linguist in the 19th century just sat down and did the calculations and came up with 1.8. And this is just the number. It's not like that. It's not physics. There's no a priori proof that's going to tell you how to make these choices. You basically have to either look at what people have done in the past and mimic what they've done and say, this is the best known thing. This is what we do. I use lambda 1.5 because that's what seemed to work in these other papers. Okay, that's the best you can do right now. There's an empirical solution, which is maybe a bit better, which is do your own experiments, try different values, and choose one using some data. I mentioned this possible pitfall because people do it all the time. They say, all right, I need to choose some hyperparameters. I don't want to use my training set because what will happen if I use my training set to choose my hyperparameters is I will probably not generalize well. If you think about using your training data to choose the n-gram history length, your training data will always encourage you to pick a longer n because you can do a better job fitting your training data with a longer n. You want to choose an n that generalizes to new data. So you say, okay, new data. Where do I have some new data that I've never that isn't in the training set? Oh, I could use my test set. Don't do it. You're cheating. You're now cheating because now setting hyperparameters is part of building your system. If you use your test set to choose your hyperparameters, then you have invalidated all your evaluations with that test data because you've now looked at the test data. Maybe it's indirect. Maybe it doesn't matter that much, but over time it will matter if we all consistently do this. And this should feel obvious. You should feel physical repulsion when I talk about this idea of using the test data, but people do it. Like you find examples of it in the literature, and it's like people use the test, or they do a sensitivity. One paper is perfectly innocent. They do a sensitivity analysis, and they say, if we had chosen these different hyperparameters, here's how the perplexity would have looked. And somebody else looks at their curve and says, oh, I know what to choose. And then they use the same test set. And now we're not doing a valid test. We're cheating. So remember, always, when you construct data sets, don't just make training and test. Also hold a development set, sometimes called a validation set. Hold aside some data that you're not going to use for training or testing so you can do this annoying stuff. The other thing I always say is that if you try these different values, you can do even better, which is to think of this as an optimization problem and say, I'm going to use my validation set and I'm going to do a systematic search or apply some optimization procedure that someone else could reproduce and maybe improve on to choose the hyperparameters. So we wrote a paper a few years ago arguing, we called it Show Your Work. Part of your work is choosing your hyperparameters, and part of the cost of building a system is that search. And you should be very transparent and clear about it so that other people know how much work went in. Okay. End rant. N-gram models, still pretty easy to understand, very intuitive. You can make them very cheap. My friend Chris Dyer wrote a book almost 15 years ago showing how to implement these things on large numbers of CPUs using MapReduce architectures and things like that. When you don't have huge amounts of training data, if you're working on NLP in a language that's really, we're more in like the millions of words, consider the language. Consider the n-gram language model. Consider that you might be able to do something much cheaper than build a modern language model, and it might be the best thing you can do for the data you have. We still have that fixed vocabulary assumption. We're still using byte pair encoding or something like that. Probably that's imperfect. That's not a perfect reflection of the way language works. We know the Markov assumption is linguistically inaccurate. This is not the way language works. Nobody who uses n-gram models believes that this is how we talk, that we just have a finite memory and just sort of say the next word. If you take an n-gram model and you generate text from it, it will sound like kind of I don't know, someone who's half asleep who's just rambling, talking in their sleep or something. It'll be it'll be like locally fluent. The patterns will sound like words, but it will not make sense most of the time. But as you increase the history length, it will get more and more realistic. And as you increase it to an infinite history length, it will be memorizing the training data. It will effectively approach that really naive model we started with. But you'll always have the data sparseness problem, and the vast amount of research that was done in building n-gram models was on that smoothing problem. How do I deal with the zeros? Okay, so this is where we switch and we say, well, what if we don't do lookups? What if we don't have a big table that stores all the n-grams that we've seen and the ones we haven't? And we don't necessarily make fixed history length assumptions. We instead think of the probability distribution over the next word as the output of a neural network. So what that means is that the parameters theta are going to do the work of taking the history and transforming it into this distribution. Okay, so I think of neural networks as simple mechanical transformations that take vectors and map them to other vectors. And usually we think of these transformations as happening as a series. It's a series of things. We call them layers. What is a neural network? This is as ubiquitous as these things are. I'm never really happy with the definitions people give, and I think the name just invites confusion. It has nothing to do with brains. Nothing. Don't think about neurons. Just put it out of your head. Okay. There was a connection in the very early days, and it's just not helpful. Okay, there's a different meaning of the word neural. Formally, think of it as a function that takes learned parameters theta and inputs, which are going to be vectors, and maps them to outputs, which are also going to be vectors. Okay, so vector functions, maybe they're matrices, maybe they're tensors, whatever, doesn't matter. Imagine we can always linearize it out and think of it as a vector. The input is a vector, the output is a vector. The key property that neural networks pretty much always have is that they are differentiable with respect to the parameters, the theta, and they are nonlinear with respect to the data input. What do I mean when I say nonlinear? It means there is not a matrix somewhere out there in the universe that you could always use instead of the neural network. You can't just take your input vector, multiply it by some magic matrix, and get the output. It's more complicated than that. It's nonlinear. That's all it means. I think the first time I gave an invited talk after neural networks rose into prominence in NLP, I tried arguing that we shouldn't call them neural networks. We should call them squash networks. Because this nonlinearity thing is usually implemented through something called a squashing function, which takes a range of values and squashes it, an infinite range of inputs and squashes it into a finite output range. It didn't stick. Right. Okay, so for a neural language model, what this means is that we need a couple of things. First, we need to take word histories, which I said earlier, these are discrete things, right? These are sequences of some arbitrary length of discrete events, and we need to somehow turn them into vectors or matrices. So we're going to call that encoding. We need to encode the history. And we also need to be able to interpret the output as a distribution over the next words. That one's not so hard because distributions over words are in fact vectors, right? They're just vectors that happen to sum to 1 and that are non-negative. All right, so I'm going to start. I'm a contrarian. I'm going to describe to you a solution to language modeling that you can find in some papers, but virtually everyone has forgotten it. And it's, it never was like a state-of-the-art model. People never really used it. There were all kinds of reasons not to use it. But conceptually, because again, today it's free, we can build whatever models we want because we're just talking about ideas. Nobody has to implement anything. There are very few laptops open, which makes me very happy. Nobody's implementing this in real time, I think. Let's just think about this as a classification problem. Okay, language modeling as classification. The history is my input. The next word is my output. So the label set for this classifier is just the vocabulary V. And so you can reduce the language modeling problem to just supervised classification. You have n instances, one per word token in your training data that you're going to train from. The input is the history. The output is a prediction of the next word, or a distribution over the possibilities. That's what we really want for language modeling. So it's going to be a probabilistic classifier. Note, the training instances are not independent. Each word has a history, which is itself comprised of words which have their own histories. Training data is not independent. I'll let you decide whether that matters. Okay. I would argue that you rarely have training data that's completely independent, as assumed by most learning algorithms. Just pointing it out. So here's a way to do it. Who's familiar with multinomial logistic regression? And I say those three words. Does that feel comfortable? And yeah, okay. Some people know it. They learned it the day before yesterday. Okay, that was not a test. That was. So I don't know. You probably saw. Everybody uses slightly different notation for this. Here's a version of the notation for language modeling. Ignore the denominator for now. This is our n-gram model, our n-gram history. If you take the history and the word that we're predicting that might come next, so this is the input and the output, and you pass them through a featureizer, something that turns it into a vector, and you can dream up whatever features you like that look at the words and map them to zeros and ones or continuous values, whatever you want. Whatever features make sense to you, but deterministically map the history and the candidate next word into feature space. And then you take an inner product of that feature vector with your parameters. You get a score. It could be any number. You exponentiate it. Now it's a positive number. And then you renormalize it over all the possible other choices you could have made for the vocabulary, out of the vocabulary for the next word. You get a probability distribution. This transformation is sometimes called softmax. It wasn't always called softmax. Whatever. It's a nice way to take a vector of numbers and make it into something that you can call a probability distribution. Okay, that is a way to build a language model. And people proposed it about 30 years ago. Didn't really stick for reasons we'll talk about, but basically, what you have to do here is you have to be clever about the features. You have to think really hard. How do I take any history of n-1 words and turn it into a vector of interesting things to note that will help me estimate the probability of the next word? Okay, you have to do what we used to call feature engineering. These models had other names. Nobody back then was calling them neural networks. I don't think. The name that was most often used in the NLP community was maximum entropy models, which is also a confusing name that I wouldn't have chosen if I had any say about it, but I wasn't in the field yet. But through today's eyes, through the information we have today, we can think of this as very much as a neural network. Notice it has parameters theta. It has some nonlinearity. It has this softmax function. That part where you have to choose the features, that's not really, that's like a lookup or some function. I don't know how you're going to implement it. But that's not really the numerical processing. That's just how you encode the input and a candidate output into a feature space. In any case, I would argue this is not so far from neural networks or neural language models. These things were not practical. Why weren't they practical? The answer is basically in this denominator. Every time you predict a word, you have to redo this calculation, pairing the history with every candidate next word. And with lookups and the ways that these feature functions were implemented, this was completely intractable with the hardware they had then. Today, if we revisited these models, it's possible it wouldn't be so bad. It's possible that there would be tricks that would make it work. But with the hardware they had in the early 90s, the mid 90s, the features they were using, this was just not, it was never going to make it in real systems. But it was intriguing. The other thing that happened was they realized in order to estimate those parameters, there's no more count and normalize. Okay, and the basic reason is that all the parameters end up depending on each other through that sum in the bottom. You can't simply count up if you have discrete features, you can't simply count up and normalize. They all depend. Everything's interdependent. The features can intersect. They can be correlated. There are different ways of saying the same thing. Ultimately, you have to use some kind of numerical optimization to solve for the thetas. The closest relative of this kind of model in classical statistics is going to be linear regression. It's very related to linear regression. So you end up with a family. They had a whole family of different algorithms that were basically solving this kind of problem iteratively, updating the parameters, making multiple passes over the training data. Eventually, the community converged for this kind of problem. Oh, it's convex optimization. We can use something like gradient descent or stochastic gradient descent. That was much later that we made that realization collectively that we could use stochastic gradient descent. And I'm not going to talk a lot about stochastic gradient descent today. You already saw it. Okay, so what made them impractical? I just gave you the answer. It was the fact that you had to do numerical optimization. It was the 90s. The computers were weaker than your cell phone today, and you had to think about the features, which some people loved and some people didn't. But you had to that summation in the bottom was really the thing that made it computationally demanding. Okay, so we have now seen our first neural language model. Again, I'm being contrarian. It's not. Some people would say it's not really neural, whatever. You've seen something that is getting you extremely close to neural language models, and everything up to this point is based on traditional principles that you could have applied to almost any problem, and we've been creeping up slowly towards what is it about language? Why is the Ngram not sufficient? How do we use the data in the most effective way? So it will be much easier if you grokked everything I gave you up till now to make sense of what's coming. So the cute little orange kitten is our multinomial logistic regression model. Not too scary. Familiar. Probably not going to fight that hard. Not particularly easy to implement. I think this is a good point to take our break. If we're at, are we close enough? I think I'm going a little fast this year. You aren't asking enough questions, so go drink coffee and ask more questions in the second half. Yes, oh, that's a good point. Sorry, that's actually a great idea. Let's take 4 minutes and do questions now, because maybe I didn't give you room to ask questions. Ask away. Why do we multiply the probabilities? Yeah. Let's take the questions one at a time. So I'm going to go back, way back.
No, you don't need it. I was just connecting one with the other. If you
I
want.
see. I see. You answered your own question.
But how do you to select and curate the data? Because you just mentioned. Take it.
How do we pick data?
And curate it, yeah.
So we could talk all day about that. So I'll give you my answer to this. We built a language model at AI2 called Olmo. You may have heard of it. Olmo is very special because it's a modern language model, and we also released the training data, the pre-training data that we use to build the model. Nowadays, when we talk about language model training data, we call it pre-training data because people do other kinds of training later on after they've trained their model. We wrote a whole paper about this. It's appearing at ACL. You can read the Olmo paper, the DOMA paper. DOMA is the data set, data to feed Olmo's appetite. And we had a few different principles. For us, first thing was we needed to be able to share the data. That's not necessarily a constraint for everybody building language models, but it was for us because we were committed to openness. We wanted to stick reasonably close to models people had built before so that when you do scientific work with our model, it's a reasonable proxy for other things people have done. We didn't want to be totally radical. We also made a commitment to English. Our end use cases for these models, the things we keep in mind, our kind of North Star, at least for many of us on the team, is scientific applications where we're dealing with scientific literature. So because most scientific literature is in English, we focused on English. We did include some code because many people had observed by the time we started that including code from programming languages is a good thing to include for many use cases. We included a lot of scientific text. But the data mix, we did a lot of experiments with much smaller models that were cheaper to see what would lead to decent performance in terms of generalization and in terms of downstream performance with different mixes, different proportions of the data. We had a finite budget for that experimentation. We couldn't do it forever. So at some point we had to say, all right, that's it. This is what we're using. This is the best thing we found. That's the short version of the story.
What do you mean by as? Is like an association, is a standardization? Because all of this is like a shared agreement that you are mentioned. We take these assumptions. Yes, thank you.
Yeah, I think, at this point in the history of language modeling, there's a huge amount of experimentation to be done, and most of the answers to what data should you use, we don't have good reasons for the answers. We just have observations. So what that means is, if you are working in this space, if you want to help the larger community have deeper understanding, you should document everything and be extremely transparent about all of your decisions. You will get it wrong. We will all get it wrong, but let's at least be reproducible so we can learn from what people are doing. Now, if you had different goals, if your goal was to build a language model that worked for many different languages, let's say you were funded by the EU and you wanted to support every language spoken in the EU, you would go about this in probably a different way. I think some of the tools you would use would still be some of the things we built, some of the code that we made and released with DOMA would absolutely be helpful. But the way you would make your decisions and your guiding metrics would probably be quite different. One more point, a quick point about curating data. People often talk about data quality and good data and clean data, and they're sort of implying that there's stuff you don't want. And there's probably a lot of things we can agree we don't want in the data. There's a lot of stuff on the internet which is just hateful, and most of us don't want that in our language models. But this is actually kind of tricky. And sometimes when people talk about good data, they mean formal language as opposed to informal language, or they want standard dialects as opposed to minority dialects. We had a paper called "Whose Language is High Quality," which looked at quality filters people were using to filter language models and found that they end up introducing biases. You can't get away from this problem. There is no unbiased data sample that is going to avoid all of this stuff. Especially at the scale of data we're looking at now, where no human could in their lifetime read all of the data, even if we had objective ways to make these judgments about what belongs in the language model, which we don't. Sorry, long answer, but I'm passionate about that question. We should go. All right, coffee, save your questions. We'll see you back in 30 minutes, I think. Thanks.
Math mistake in the
I had a math mistake? Well, tell me later when we're not on YouTube. What was it?
So they have exponential and they have log base 2. So
Oh, you're right. It should say x base 2, or it should just say 2 to the. Yeah.
no big deal.
No, I saw some typos too. All right, I'm going to turn off the mic. Okay, let's get started. Thank you for coming back. I'm not always sure what's going to happen. So where we left off, you saw multinomial logistic regression as a way to do language modeling, essentially treating the next word prediction problem as a classification problem and applying what was for a while kind of the most popular classification technique, at least in NLP. What's going to happen next is I'm going to give you kind of a parade of neural network approaches to language modeling. It's not exhaustive by any stretch of the imagination, and anybody who is familiar with the subject matter is probably going to be disappointed that I didn't go into more detail about their favorite model or the one they think is most important. What I want to do is give you just kind of a taste of the different ways of thinking and assumptions and the developments as they happen. So you kind of appreciate how we got where we are. I'm not going to, like I said, I stopped just before the transformer. So there's no secret. The transformer is now the thing that dominates. There are alternatives. You can understand some of those alternatives better if you understand the background that I'm going to give you. You can understand the transformer a bit better if you understand the models I'm going to give you. But I'm really giving you just a taste of each one. We don't have time to go into a ton of detail, and I think it's more important to get the high level information. Everything that I'm showing you, by the way, was used for more than just language modeling. All the techniques, all the different kinds of neural networks, they've been used for many different problems in NLP and even beyond. And this happens all the time. We see a technique get introduced for one problem, it gets used for many others. I think separating the techniques from the tasks often has some benefit. Grounding them all in one task, like language modeling, also I think has a benefit. But what I really think is the most useful thing is to understand the similarities and differences. It's not like, oh, it was feed-forward networks, and then they all got canceled and went away, and we moved on to a different thing. All of these things kind of coexisted. They influenced each other. And understanding the pros and cons of any one of them in a given situation will make you much, much more capable of absorbing the new things that will come next year that none of us are expecting yet. Okay, so I think in order to make sense of what comes, there are two key developments that you have to appreciate. The first one is going to take a little more time than the second. The first one is treating words as vectors. So moving away from the idea of feature engineering and instead thinking about as a key part of our model, every word in the vocabulary maps to a vector. That is a central idea that I think took a long time to develop in the field. The second one, this is really easy. Deeper models, more layers, more complicated functions, more nonlinearities, more linear transformations. These things we've tended to see an increase over time in the depth of the models, and that tends to give you a wider set of distributions you can represent. It's a way of, it's like increasing n in the Unigram model. It's just giving you greater capacity to represent more of the phenomena, and that helped. No surprise. This is why people call it, this is what deep in deep learning means. It means more layers. One thing that stays the same, fortunately, and we don't have to talk about again, is that you're still using stochastic gradient descent or something very similar to it to maximize likelihood. That principle is throughout the rest of the lecture. It's still there. Using optimization techniques, whatever the best thing is that we have at the time to try and find at least a local optimum of the likelihood function, that's just fixed. I'm not going to talk much about that. The one thing that will change going forward is that the likelihood function won't be convex anymore. I didn't really say a lot about this before, but when we started with the Unigram models, we basically had a closed form solution to maximum likelihood. It was counting things up and normalizing appropriately. When we moved to the multinomial logistic regression model, I pointed out that we didn't have a closed form. We had to run some kind of optimization problem. It didn't matter too much how we did that. It was mostly driven by efficiency, because the function we were optimizing, the likelihood function, was convex in the parameters. So no matter where you start, if you keep going up the hill one way or another, if you go long enough, you're going to get close to the top of the hill. With all the models from here on, it's not one big hill. It's more like a mountain range. Or actually, we don't really know what it looks like. We don't know how to visualize it. It's too many dimensions. We just know that where you end up, even if you find a local maximum, it depends on where you start. And so this gave people a lot of worries for a time. Now we never talk about it, but it is true that if you reinitialize your model and start training again, you'll probably get a different solution. Generally, people don't worry about this too much. They've come to the practical conclusion that finding something close to a local maximum or moving in the direction of a local maximum for a while, even if you don't get that close, works in practice. So that's one gap between sort of theory and practice that maybe you should keep in mind. Okay, let's talk about word vectors. The simplest way to think about words as vectors, remember for a neural network, eventually you need to get your input encoded in some continuous vector form. So how do we do that from words? Well, the first thing you can do is you can say every word in the vocabulary is going to get a unique vector, and we want to have a lot of power to represent words differently. So a very simple thing you can do is say, well, I'm going to have a v-dimensional space, and every word is a vertex on the unit simplex in that space. So basically, every word gets a dimension, and it has a 1 in that dimension and zeros everywhere else. And now all of the different words in the vocabulary are orthogonal to each other and separated in this high dimensional space. We call these one-hot vectors because one element of the vector is hot. So if you have a vocabulary of size v, you need v dimensions. Okay, this is the starting point. Usually what happens in a neural language model, v dimensions is a bit too many. And because we think, words are not, the way we tend to think about words and languages is they're not all that different. Some words are actually quite similar. Some words are just, different spellings of the same idea. Some words are synonyms. Some words are related. Maybe what we could do is think of each word as having an embedding in some, word space. And so what we do is we multiply the one hot vector by a matrix. We'll call it M, the embedding matrix. And that projects us down usually to fewer than v dimensions, usually to some, I don't know, for a long time it was like 300 was the standard number. I'm not even sure what it is in current language models, but some, few hundred or thousand dimensions. And so this matrix of embeddings, when you're selecting one word vector out of that matrix, it just becomes part of the parameters. So these are just more theta that you're going to learn, and so this is just an incredibly powerful idea. They're sometimes called dense word vectors as opposed to the very sparse ones that we used when we were one hot. But people have connected this idea of embedding words in a vector space back to ideas in linguistics about word meaning, and the idea that words can be closer or farther apart in meaning. Maybe there's a direction in that space where like Sunday, Monday, Tuesday, Wednesday, Thursday are all kind of like, I don't know, in a row or in a circle. I don't know. Like words have meanings and the meanings are related to each other. And that's an old idea in linguistics. And people have tried to draw connections between those old ideas in linguistics and word vectors, which I think is cool. So word vectors are a whole topic, right? And for a while there was kind of almost a subfield within NLP of how do you make word vectors? Just that was a useful idea on its own, not even thinking about neural language models at all. But they are a prerequisite for building a neural language model. But the idea was completely separate. It came up in the early 90s, separate from language modeling as kind of a computational linguistics concept. We could spend an hour on it. And in fact, there's a completely different way to teach this lecture where we start from word vectors and word representations and work our way up to language models. And so I wrote a review article about 5 years ago that you can find online that takes, I think it's called putting words in context or something like that. Anyway, you can find it. It was in the CACM. If you want kind of a different buildup, that's a path you could take. But here we focus on sequence models. So anyway, people started coming up with ways to just build word vectors. They usually started from co-occurrence statistics. So here's a word v. How often does it appear just after or just before some other word v prime? We collect a lot of these kinds of statistics. We compare them and to what we would expect under a simple or Unigram model. We look at things like mutual information. You can also think of it as a predictive modeling task. If I know the word at position I, what is a word nearby? That feels a little bit like language modeling. And so there were these popular methods. They had names like continuous bag of words and skipgram. There was a package called Word2Vec. People use Word2Vec, or Glove was a successor package. These things looked a little bit like neural classifiers. They were trained in similar ways. You can actually show that they all basically amount to some variation of taking a big co-occurrence statistics matrix of words and doing some kind of factorization on it, or some compression or something like that. But basically, and for a while, it was very common to start with those words, like run one of those algorithms and take the word vectors and use that to start off your language model. And so the first part of the language model would be the lookup of every word in the history, and that embedding matrix could be learned using one of these standalone metrics. Today, what we typically do is just say M is more parameters. It's just the first part of the model. We initialize it randomly, and while you're doing stochastic gradient descent and training all the other parameters of your language model, these word vector parameters are also getting updated. But you could pre-train it. You could plug them in and just leave them alone. You could plug them in and fine-tune them and update them alongside the other parameters. All of these things have been done. I point out this pre-training idea just to first point out that the idea of training one thing and then using the parameters into another and plugging them into another model and then continuing training, it's an old idea, very old idea. It is not, the idea of pre-training a language model was very natural and unsurprising to the community when people started proposing it, because we had been doing this kind of thing for a long time. And the attraction is that maybe it's cheaper, right? If it's very cheap to get your word embeddings and you can just freeze them or just do minimal updating of them later, it may speed up your whole learning process. So just as an engineering consideration, something to remember. Okay, so that gets us part of the way there. We have words from the vocabulary. We transform it into a sequence of word vectors. So every token is now mapped to its word vector. And then the name of the game in neural language modeling is to somehow figure out how to take a variable length input and plug it into a neural network that can predict the distribution over the next word. Because the length of the history could vary. We've seen this before. We saw this with when we talked about pre-neural language models, and so keep that in mind. The one additional thing we have to say, that the other major development, again, very easy to understand. How do you make a neural network more powerful, more interesting? Well, you just add layers. And so neural networks, in very broad strokes, they tend to look like the following. You alternate between two things. You have affine transformations that take a vector, multiply it by a matrix of parameters, maybe add another vector to that, and then you get a new vector, possibly of a different size, possibly longer, possibly shorter. That's one option. The other is to do something nonlinear. And usually we see models going back and forth. The nonlinearity could be something like the softmax we saw earlier. It could be an element-wise function. And in fact, very frequently it is, where you take like a hyperbolic tangent or something called a rectified linear unit. Usually what these nonlinear functions are doing is they're taking inputs that could be from positive to negative infinity and mapping them into a range that's fixed at one or both ends. So like the hyperbolic tangent takes things, this is the hyperbolic tangent. Anything from positive to negative infinity goes in. Most values that are large in one direction or the other will get mapped very close to one. Everything in the middle kind of spreads out between -1 and 1. New things get introduced. Since I made these slides, I think there have been new nonlinearities. This is, choosing which nonlinearity is going to go into your neural network is one of these hyperparameter decisions. I don't think, if there are theoretical or a priori reasons to like one over another, I don't know what they are, and I'm skeptical. But basically that's it. Somehow your neural network is going to alternate between some kind of affine transformation and some kind of nonlinearity. The transformer, no exception to that. Everything we're going to see today involves these same things. And generally what happens as you add more layers, particularly the linear transformations, are going to give you more parameters. More parameters means it's more expensive to run your model, to estimate your model, but you have more knobs to turn. And so maybe you can do a better job of fitting your training data. And by extension, potentially, maybe you'll get better generalization, which is what we hope for. Remember the picture, right? So now we could add the cheap thing to do when you go neural, if you want to add more model capacity, is to add layers. And this was, I don't know, there was a period of a few years where that was like the joke at conferences. It's like, we're going to go to 4 next year. Just more layers. Wow. Okay. All right. So the first thing you can do, we have a variable length history. Could be any number of words that came before. We already knew from n-gram modeling that longer was generally better. But the first thing people started doing in earnest when they wanted to build neural language models. And then at this point, they were consciously saying, we're going to use a neural network to build a language model. This is 10 years after the sort of multinomial logistic regression stuff we talked about before. The idea was, let's not mess with the n-gram assumption. We'll still build an n-gram model, but instead of using handcrafted features of the history, let's use a neural network to encode. And so yes, this is ugly, right? I tried to make it a little less hard to look at by coloring the parameters pink, and showing you where the word vectors are by calling them M. This is my notation. This is not from the paper. And I also tried to label, this is an affine transformation. This is a nonlinearity. This is another affine transformation. This is a nonlinearity. That's it. This is the whole thing. You start by looking up each of the n-1 words in the history. So MHJ is the jth history word. You are going to use that twice. In one place, you're going to multiply. You're going to do an affine transformation with T and U. In another place, you're going to do it with A and B. The first copy, you're going to then run through a nonlinearity, through a tan H, and multiply it by another matrix and add it to the second copy. The whole thing finally gives you a vector, which you push through a softmax, and that's your distribution. That's the whole thing. That's the model. Very simple. I guess you could argue this is, you could say it's 4 layers. I think usually people think of a layer as being the affine plus the nonlinearity, so maybe it's 2 layers. You have to make some design choices. You have to decide how many dimensions there are in your word vector and how many dimensions there are in those intermediate representations. So we call that H. The dimensionality of the thing that comes out at the end has to be V because you're running it through the softmax. You have to have one value for every possible word. Here's a computation graph for this model. So the first thing on the left is your 1 hot vector representations of your 5 history words. This is a 6-gram model in my notation. Yeah, it's a 6-gram model. I don't think that's what they used in the paper, but that's what's in my picture. Each of those gets transformed into a smaller embedding. The embeddings then go through all these layers, which eventually get you to the softmax, and that's going to be a distribution over the next word. And there's your neural language model, 2003. So I look at this through today's eyes, and I think this is basically multinomial logistic regression, but it has 2 kinds of features, and they were lazy. They didn't want to engineer the features. So they used word embeddings as the features, but they also ran those word embeddings through some learned transformation that involved an affine and a tan H. And so they got these new parameters. Alongside the embeddings, they have the weights in the affine transformations. These parameters are very different from the parameters in the n-gram model. In the n-gram model, you could pick out a parameter and say, this represents my estimate of the conditional probability of the word lecture after a history like early on a Saturday morning, Noah decided to give A, right? You could interpret that parameter. You cannot interpret any single parameter here. There is no easy way to pull a particular knob out of the system and say, this is what it does, right? This is the thing that I think held back the adoption of neural language models in NLP for a long time more than anything else. We as a community were very uncomfortable with models that had parameters that didn't map onto our intuitions about the world. How many parameters did it have? Well, you multiply together the size of all those matrices and vectors that went in. I do the math on here. With a vocabulary at that time of about 18,000 terms. There was a thing we used to do where any word we didn't know, we just called it out of vocabulary. It's like, this is pre-byte pair encoding as a tool in NLP. So if you saw a word you didn't know after splitting, you said this is an OOV and you estimated probabilities for that, so you could have whatever vocabulary you wanted. In any case, once you made the choices they made in this paper, you ended up with a vocabulary that was with a number of parameters D that was linear in the vocabulary size. And they were doing 5-gram models, so my picture was slightly misleading. What that means is that they had far fewer parameters than classical n-gram models. They also did not have to worry about smoothing, because one of the beautiful things about the softmax function is that as long as your inputs are finite, the outputs will all be strictly positive. None of them will be 0. So the smoothing thing kind of went away. They did an ablation where they forced one of the larger matrices to be 0 and eliminated 300 times via the parameters, and that actually worked better, but it was slower to converge. So this is a really early example of a trade-off that we sometimes see where you can add more parameters and it might speed up training, which is maybe counterintuitive, or you might be able to train with less iterations, but it may not lead to ultimately a better model. More parameters doesn't always mean better model. There were also some other things where you could eliminate parameters by just taking simple averages rather than concatenating, and this related to some other models. This isn't super important now. What is important is like, why did this work? Why was this? I think, you know, a lot of people had a lot of feelings about neural networks in the early 2000s. And I think it was kind of surprising that it did work. And I think the story that we tended to tell at that time was, well, what they're doing is they're basically learning feature combinations that you wouldn't get with one of those old multinomial logistic regression models, which is basically linear except for the softmax at the end. So you're learning, if there are features in the word embeddings, you're learning to multiply them by each other up to a point and get interdependencies among them. And what's happening when you're learning in this by doing stochastic gradient descent is you're doing some kind of like smooth exploration of many features that are sort of conjoined or more complex than the ones we had with just the word vectors. Today, what we tend to say is, well, when you optimize the whole thing for next word prediction, when every parameter in the model was tuned specifically to get the model to be good at predicting the next word, and they're all tuned together, the way we represent the words, the way we represent the histories, everything is being kind of literally optimized to do well at next word prediction, we shouldn't be surprised that it's really good at next word prediction. Word embeddings were really, really important to this, recognizing that some of the parameters, a significant number of the parameters, should be dedicated to just representing the atomic units of input. That's critical. That hasn't gone away. That's still with us in all the models we use. Okay, we don't have to talk much about training because we just use maximum likelihood principle, SGD, same thing we did with version 0. It was more expensive. It took them several weeks. At this point, people were not using GPUs to do neural network training. So 40 CPUs, 3 weeks. That was a long experiment. At that time, 40 CPUs was a lot. Also, I'll just repeat, the log likelihood function they were optimizing when they built this model was not convex. So what the practical thing that means is that when you evaluate the language model, you are evaluating not only your modeling decisions, but also the way you initialize the model and the algorithm you use to estimate it. Whatever technique you used, however you decided to do SGD, your batch size, your learning schedule, all those little choices that you make when you actually run the algorithm, all of that is part of what you're evaluating. And if you changed any one of those, it could have an effect on how well the model works. So it's like the whole package, not just the modeling architecture and the hyperparameter choices that were obvious, but also all this learning stuff. Okay, so let's put this under the microscope. What do we think about this model? Well, one thing that what's interesting about this is that it sort of represents each history word and it runs it through a transformation, but it treats each one differently with its own parameters. But there's nothing in there that says this is a sequence. And maybe the words that are most recent are going to be more important to the prediction, and the words that are farther away are going to be less important. All of that has to be learned, which it probably can be, right? You have a lot of evidence that nearby words are more predictive, so it's probably fine to automate that. You have to choose some hyperparameters like the dimensionalities of the words and the hidden units. Again, I don't think there's any, what is the true dimensionality of word representations in English? This is not a meaningful question. There are no word vectors, right? They're not real. It's just a model. But you have to make a choice. You can't be dimensionality free. We can't interpret the models. The architecture, I don't find it intuitive. If you do, you should see a professional. But Perplexity got better, and it was the number of parameters was smaller, and both of those two things were kind of memorable. I think the Perplexity reduction was what really got people's interest at that time. So the feed-forward network, it's larger than the multinomial logistic regression one. It has more layers. It's harder. I think it's harder to understand. The features are no longer interpretable. It uses word embeddings, but it's still a cat. Still an orange cat. Okay, so the feed-forward network again made this sort of bounded history assumption. And if you're fine with this idea that each position is kind of have its own features, okay, this is great. But this should bother you if you have a little bit of an appreciation for how language works. There's nothing special about the word 4 positions back. When you go to study a new language, you are almost never going to hear a rule of the grammar that says count back 4 word positions and look at, and agree with the word that is there in inflection in some way, right? There are a couple things like V2 in German, but that's German. Of course, there's always an exception, but generally speaking, absolute and relative positioning of the words is not the thing most of the time. And the other thing about this is that it doesn't scale to really long sequences. So imagine that we were just going to keep building these models up and making them, we get more and more data, time progresses, the internet's getting bigger, we can build on larger and larger collections. What are we going to do? Have parameters specifically tied to 974 words in the past? That seems wrong. It feels like we should be able to reuse some of what we learn about any given position about other similar positions. So the other thing that this model doesn't have is any explicit notion of like words combining locally with their neighbors to form bigger meanings. This is something we call compositionality. It's an old important idea in both AI and the study of language that we build more big complex things from smaller parts. Okay, so what we're going to do is talk about 3 different families or styles of neural networks that do that reuse parameters to encode arbitrarily long sequences without having the number of parameters blow up as that sequence gets longer. So the first one is called a convolutional network or a sliding window. So take the entire history of the word and start by representing it as the word vectors for that history up to t-1. We're going to predict the word at t. And what we're going to do, we're going to think in layers. Again, should be comfortable with this. Neural networks iteratively refining a representation of each of those words by building a new matrix. So this is x0. This is the first level representation. The next layer, x1, is going to be a function of these. We're going to apply something called a convolution function to this matrix. And you can think of each of the vectors in that new representation as being a new way of representing the history word at this new layer. So here's how we get to that second layer. You're basically taking the first layer and you're multiplying it by a matrix. That C is a parameter, and you're kind of sliding the matrix along and doing a calculation for each position in the new matrix. I'll show a picture in a second, but what I want you to see first is that this is an affine transformation of the previous layer, and then we apply a nonlinearity like tan H. And your hyperparameters are things like the width of the sliding window, and so this one operation is called a filter, and the M's are the word positions. So you have to choose the number of layers, you have to choose the nonlinearity of each layer, you have to choose the width of the sliding window and how many filters you have. But this is basically what it looks like. Down below is x0, which is the word embeddings. And then the different colored blocks are different parameters, different filters that I'm applying. And I'm applying them first to the first few words. Then I move it to the right, and I kind of slide it along and generate new representations of each word at each position in the history to get the second round. And I do this many times. That's called one convolution. I do it d times to get to the final deepest representation of each of the words in the history. And I still have a matrix. I have to somehow transform this into a vector so I can get a distribution over the next word. So I do something called pooling, which means I either take an element-wise max or I average the vectors usually. Finally, at the very end, those things go through a softmax to give me a distribution over the words. So this is very simple. in the sense that it's just affine nonlinearity. Affine nonlinearity. It takes instead of thinking of lopping off and ignoring the farther backwards in the history over here to get a finite size, we're doing a convolution. We're applying this sliding window function over the whole thing repeatedly at each layer. One thing I want you to notice about this, if you think about the computations that are required for encoding the history of word t, and then moving ahead one step and encoding the history of word t plus 1, do you see any tricks we could use? Do you notice anything in particular? Let's go back and look at the picture. What happens when I move to word t plus 1? I now have one more word in the history. I have one more vector right here. So some things are going to change, but only at the right edge. Most of the computation I did before, I can reuse. That's huge, right? Anytime I can reuse work that I did before, I want to take advantage of that. That's a good thing. And so as your sequence gets longer, you have to redo only the applications of the functions that depend on the right edge of this. And so depending on your sliding window, you don't have to go back more than that, right? This is quite nice. And that's something that we want to look for in any neural language model. We want to see ways of reusing any of the calculation during training, at least, and ideally during inference as well. And that wouldn't have been available for the feed-forward neural network, because every time you moved forward one step in that model, that earlier model, the parameters got multiplied by each word. Different parameters were going to be multiplied by each word vector. So you had to redo everything from scratch. Here, you get to reuse a lot of your work. So it's good to be lazy. And in fact, convolutional neural networks originated not for sequence models at all. That's not fair. They originated, there are versions of them or things that are very close to them that originated in computer vision as well as in speech recognition, which is definitely very sequential. But usually people remember including me, the computer vision versions first. And they were designed to be very efficient for visual processing. You can find a few papers that use them in NLP. The one I remember most is now 10 years old, and it was for text classification, but people did try them for language modeling. It never really caught on. And I think the timing just wasn't quite right. And there was another thing that sort of did catch on more so. And I think people tend to all glom onto the same idea. But if you look in the literature, you can find lots of variations of convolutional networks that try to. There's this idea of a stride where at deeper layers you skip over more of the words, and so you get effectively longer windows without necessarily doing more computation. But basically, if you wanted to keep pushing on this, the way to make it work better is to allow a certain amount of flexibility in looking farther back into the history without exploding the number of parameters. When people defend convnets, they usually point out that they are fast. The operations are pretty efficient on the hardware we use them on. And so that's why they were so beloved in computer vision and really dominated for a long time in computer vision. So it's a fast version of the cat. Okay. So the thing that really did dominate for a while, and the most recent predecessor to the transformer, is the recurrent neural net. So the recurrent neural net also makes no Markov assumption. It's also taking the entire history going back all the way to the beginning of the sequence, at least in principle. And the idea here is, yes, you do this with the convnet too. You're really encoding the whole history, however long it is, into a single fixed length state vector. But you're doing it in a very deliberate way that uses the state vector from the previous time step to get the new one. So you're just being very explicit that the state vector at time step t-1 is a direct transformation of information that we have before that. So how does it look? Let's start at the bottom. The state vector at the beginning is just 0. We haven't seen anything. We have no information. Just call the vector 0. And then at each time step, we are going to define the new state vector at time step I by taking the word vector, the most recent word that we've seen, and also the previous state vector from the previous time step, and putting those through an affine, can essentially concatenate an affine. So each gets multiplied by a matrix of parameters. You add some bias term C, and you pass it through another nonlinearity. This is the sigmoid. It could have been a tanh. It could have been something else. And then when it's time to make a prediction about the next word, you take the previous state vector, and you do an affine and a softmax. So you've got this recurrent calculation where each state vector depends on the previous time step. And whenever it's time to predict a word, you do a little bit more work. You do an affine and a softmax, and you get your distribution over the next word, which is the output of the neural net. This is the simplest version of the recurrent neural net. You can add more layers. You can add more transformations. You can do more interesting things here. We'll say a little bit about that. But this is where it starts. What's really, I think, interesting about this, so here's the computation graph. There's your word going in on the left as a one hot vector. That's just the most recent word that I'm showing. I'm assuming that you already have the state vector from before. So the word becomes a word vector. It goes through transformation. All of this goes through a linear transformation, a sigmoid. And then if I want to make the prediction, I push that into a softmax, and I get my distribution over words. Meanwhile, I do another calculation to get the next state vector for the next time step. If I unroll this across many time steps, this is what it looks like. And what you should see is that the depth of the network, in some sense, is the depth of the history multiplied by how many layers per round. This didn't work quite right out of the box. These models had been around since the 90s. And there was a well-known problem long before people were using them for language modeling. There was this problem that when you have these really, really deep networks, the depth is the length of the sequence. What happens is that when you calculate the gradients, as you go farther and farther back, they kind of wash out and all go to zero. This is called the vanishing gradient problem. And so it's really hard to actually make any updates to the parameters in the distant past because the gradients just kind of go to zero. Another issue is that the state it's like the model tends to forget. It tends to not hold on to information and just sort of like change the state at every round. So people started, playing around with different variations. One thing you can do is you can stack the functions and make deeper networks, which gives you more flexibility. That doesn't help with either of these problems. It does help if you take the output of each layer. I don't want to get into that. There were lots of tricks. The one thing that probably is most important to remember about this time was a sort of rediscovery of an old model. So there was this model called the LSTM from the late 90s, not for language modeling, for other problems. And in 2012, people were like, let's try this. This was a way to solve the vanishing gradient problem that basically it's called gating. The idea was that you always carry some information forward. And you decide on the fly how much you're going to carry the old information forward and how much you're going to forget. So you're kind of more explicit about what you're forgetting. And so there's more parameters, and if I wrote out the formula, it would be it would have more lines and more extra intermediates. I didn't think they were particularly intuitive myself. There's a tutorial from Ola 2015 that a lot of people liked that tried to visualize it. There was a simpler version called the gated recurrent units. But basically, these things ended up working a lot better. And I think it was basically because they were more deliberate and more parameterized about what was forgotten and what was carried forward. And that stuck. The LSTM, for about 5 years, you couldn't read an NLP paper that didn't use an LSTM. Almost. It was just pervasive. It was like, this is the way we're going to do everything. And so the LSTM established the dominance of neural models in NLP. It was at this point that really most work that was trying to drive forward on performance on tasks was switching to using some variant of LSTMs. And for up until the introduction of the transformer, this was really the dominant thing, not just for language modeling, but for most problems in NLP. So that's where I'm gonna stop introducing new models. I want to point out that all of these were borrowed from other areas of AI. For example, ConvNets were really a computer vision thing. Their siblings were really a speech thing. None of them were designed to think about what makes a sequence language and not just data. I think the recurrent neural net maybe comes the closest to maybe encompassing some implied theory of how language works that makes some sense. But none of them was particularly satisfying, and I think that created conversations in the field about where we were headed and how things worked. The other thing that was happening as we moved through this sequence of models is they got increasingly expensive. To train one of these models from scratch became harder and harder, and that trend continued with the transformer for sure. So the transformer, just to kind of put it in context, it was introduced in 2017. I'll say a little more as we go on about the context in which it came into being, but I'm not going to teach it to you. I think you're getting it tomorrow. I'm looking at, yeah, I think you're getting the transformer tomorrow. Day after tomorrow. Oh, right, tomorrow you get a break. Tomorrow you get to contemplate a world without transformers a little longer. You'll be hungover from the banquet, so you'll be contemplating other things. Okay, so far we've been focusing on this abstraction of modeling where we have a sequence of words up to a point, and we're predicting the next one, and we're composing these factors of each word given the previous ones to give a score over the whole sequence. So this makes perfect sense if it's autocomplete. But what if we have an input? What if the task isn't really just continue? It's like here's an input. Maybe it's a sequence. Maybe it's a picture. Maybe it's something else. And I want to transform it into an output sequence. So this abstraction, sometimes called sequence-to-sequence models, sometimes called encoder-decoder models, as opposed to what we've been doing, which is just a decoder-only model that just decodes, just produces words in sequence. This is more about a conditional distribution over a sequence Y given some input X. And for today, I'm just going to let them both be sequences. Doesn't have to be that way. If you're doing image captioning, X might be an image. If you're doing speech recognition, X might be audio. The driving application for this was machine translation, which holds a special place in my heart as I think the kind of holy grail of natural language processing. Many things that we build in NLP, we can have long discussions about whether they're useful for humanity. Automatic translation, I don't think we need to have that discussion. I think the benefits of effective translation are pretty clear to most people. This would increase our capacity to communicate with other people if it worked. It's getting better. It's better now than it was. But so we call it machine translation. It's an old problem. It's one of the oldest problems in computer science. As soon as people started spying on each other with electronic things and using computers in understanding the world, it was like, oh, maybe we could translate and understand what the Russians are saying or whatever, the Americans, whoever. So the sequence-to-sequence family of approaches that we'll talk about next was developed for machine translation, and we're going to focus on that as a working case. But it's been used in many problems in NLP. There was a period where it felt like people were just trying to throw sequence-to-sequence at everything. That's what we do in this community. We find something that works well for one problem, and then we throw it at every other problem and see if it sticks, and sometimes it does. But here's the idea. Let's talk about machine translation. And I told you earlier, when I talk about a problem, the first thing I want to talk about is how do we know we solved the problem? I made a glib comment about machine translation doesn't work. Let's talk about how we would know if it did. So the old intuition, the way we've always, as far as anyone can remember, talked about high quality translation from computers was that you had to do two things. You have to make output that is fluent in the target language, and it has to be faithful to the original meaning. How do we measure that? Okay, we can talk about that all day. The very, very old answer is you have humans who can read the input and understand the output, sit down and make judgments and say, on a scale of 1 to 10, how fluent is this? On a scale of 1 to 10, how faithful is this? Or maybe qualitatively list the errors. You can imagine doing this if you have the right experts. Human evaluations are still probably the best way at the end of the day if you're building a real system to understand what your system does well and what it doesn't. I still endorse that for machine translation, but that's expensive and slow, and you might just want something quick and cheap that will give you a signal as to whether you're moving in a good direction. And so about 20 years ago, people started saying, what if we could automatically evaluate translation output and measure how good it is? And so they came up with a very simple thing called the BLUE score, which says, okay, I have a test example that isn't in my training data. I have a human reference translation together with the input. Maybe I have multiple reference translations from multiple humans, because most people in this room are probably at least a little bit more than monolingual. We all know there's more than one way to translate everything. And so if you have multiple choices, maybe we can do a better job of evaluating. And then you basically look at the n-gram precision. So look at all the different n-grams in your reference, all the n-grams in your system output, compare them to each other, and say how many of the ones that I put in the output were also found in a translation from a human. And there are some variations on this. There are some different choices you can make, but essentially that's the core of it. You have different n-gram lengths up to some point, I think maybe 4. And this was like a reasonable proxy. They found it kind of correlated with humans. There's been a huge amount of research over the past 22 years since we had the BLUE score. People have come up with better things. A lot of work actually done here in Lisbon on this problem. I'm giving you the sort of jumping off point, and there's an extensive history here. But essentially what we have now are various automated scores that approximate the human thing in a cheap way. So that's the short answer to how we evaluate machine translation. It's not quite as cut and dry as Perplexity. You have to develop a score and commit to it, and you need some data that humans have translated, but that's essentially it. So the next question is, how do we do it? How do we build these kinds of systems? And I think one of the most interesting insights about this was in the 1940s. I know, this is crazy. I will be shocked if you see a reference to anything earlier in the rest of the Lisbon Machine Learning Summer School. So these were 2 of the early researchers in information theory. And Warren Weaver wrote to Norbert Wiener, who we were just talking about before this. He got his PhD at 18. Anyway, so the recipient, the writer of the letter, Warren Weaver, says, one naturally wonders if the problem of translation could be conceivably treated as a problem in cryptography. When I look at an article in Russian, I say, this is really written in English, but it's been coded in some strange symbols. I will now proceed to decode. Okay, so this gave birth eventually to an idea called the noisy channel model. So this is a pattern. The noisy channel model is not a specific model. It's not like the feed-forward neural language model of 2003. It's a more general idea. It says, I have these 2 random variables, x and y, and the story I'm going to tell about them is that first y was generated from something called the source model, and then it went through something called a channel and got transformed and changed somehow into x, which is what I observe. So y was the true message. It was the plain text. It's the thing I really want my system to ultimately give me as an output, even though in the story it came first. It's the thing I'm trying to reconstruct. X is the encoded version, the ciphertext, the garbled message, the observable evidence, the input. So this always trips people up a little bit. The output came first. It got garbled into the input. My job is to decode, to go backwards through that process and reconstruct the most likely y given x. And the key tool that I use to get there, to maximize the probability of y given x, is I apply, what is this rule? What did I apply? Bayes' rule. We use Bayes' rule. We don't need to worry about the denominator because x is fixed. We care about these two quantities. How likely is this output how likely is the input that I'm looking at given this candidate output y, and how likely is y a priori, the source model? When we apply the noisy channel model to something like translation, we usually call this the translation model, and it models the probability of the input given a candidate output. And we call this the language model because it's just the probability of good outputs. That's the fluency score. So to write it a slightly different way, again, we evaluate translation on faithfulness and fluency. If we're mapping a French word sequence F to an English word sequence E, then we want faithfulness to F. That's the channel model, the translation model. And we want fluency of E. We want good output. And that's what the language model is doing for us. Okay, so the key thing that that you need to put this idea to work is, of course, the data for the channel model. You need to have sequences in French and English, or whatever language pair. Originally, it was French and English, and we'll see why. And so the idea is that if you have enough examples of French and English paired that were translated by people, you could hold some of it aside as test data and use your BLEU score, but you could also maybe estimate this conditional distribution of probability of French given English. In a noisy channel translation system, we could use this together with a language model of the output language, in our case English, to decode for F into an English translation. And this was the original proposition about how we would build machine translation systems from data. So where are we going to get this parallel data? Where does that come from? Any thoughts? Maybe somebody knows the history of where they found it first. Bible, yes. Bible was not the first thing. No, before the European Parliament. I don't think when they started doing this, the European Parliament had digitized proceeding. No, the Rosetta Stone is tiny, and we don't know how to decode it. So, technical manuals. People did look at technical manuals. The first thing is actually our friends in Canada. Bilingual government. Everything done in the Canadian Parliament has to be done in English and French. Everything gets translated. It was called the Hansard data because I think that's the company that produces the parallel text. Somehow these guys at IBM made a deal and got the digitized version of the Canadian Parliament proceedings in English and French. So that was why they did English and French first. The European Parliament stuff came, I think, quite a bit later. I want to say it was the mid-2000s. The Bible, people did start looking at the Bible fairly early on because it's in many languages, but it's actually pretty small. It doesn't look small, but it's not that much text. It's also, there's a problem with the Bible, which is that it's very out of domain for most of the things we want to translate, right? If you, like the fluency score might really strongly prefer that you talk about wars and who begat whom, and it's, the content may not be safe for whatever. Okay, so I'm going to give you the history of pre-neural machine translation in one slide. We could talk about this for a long time. It's a fun and interesting topic, but I just want to give you kind of the quick montage version. So very early, going back to not long after that letter from Norbert Wiener, people viewed this as essentially, this was before we had really powerful computers, and computer science was kind of developing, and the idea of formal automata that could translate, that could take an input sequence and generate a translationally equivalent output sequence was fascinating to people. And for a long time, from the 50s up through, let's say, the 80s, it was really what automata, what rule-based systems could do translation. If you have word-to-word mappings, how can you build those up compositionally to tell a story about how you're going to map from inputs to outputs? They were much more focused on linguistic theories of language and expert crafted rules than they were on the noisy channel. The noisy channel came back into translation in the early 90s with some key papers by these folks at IBM, who introduced a series of models, memorably named IBM Model 1, IBM Model 2, IBM Model 3, up through Model 5. And this was really the beginning, I would say, of getting statistical methods and machine learning ways of thinking into NLP. And it transformed the field across not just people working on translation, but it changed the way people thought about most problems in NLP. And that, I think, was the big revolution that shifted us to thinking about data as the way to solve NLP problems. This stuff had limited practical impact on others' work until there were open source implementations. and automatic evaluation. So late 90s, early 2000s, it was much easier to get your hands on code that would estimate the models. You could run them on your own data. You could evaluate how well you were doing. And that really kicked off work on machine translation. So in the early 2000s, there was a lot of experimentation, people trying a lot of ideas. And what everyone realized pretty quickly was that you couldn't think of translation as a simplistic word-by-word production process. You really needed to get a lot more of the context in. You had to look at what was going on earlier in the sequence as well as in the other sequence to solve this well. And there were two major ways of thinking about it. One was just, it's kind of like n-grams. Larger chunks of words, not words, is what we want to model. Word sequences of up to like 5 or 6 words is the level of granularity we want for remembering how things translate. Sometimes with hierarchical organization, sometimes not. The other one was to try and use this idea from linguistics of a syntactic parse tree. So if you parse the input, or maybe parse the output as you're constructing it, or maybe you have trees over both, this will help you generalize in a better way. And these two ways of thinking were mutually influencing each other. They were in friendly competition, and there were a ton of papers. You can read some good overviews from like 15 years ago now. In the meantime, in the background, there was this fringy idea that was brewing that most people were not paying a lot of attention to. The earliest paper that I know about was in the late 90s, but around 2013, it really caught on. Let's use neural nets. And there are a couple papers that sort of found the starting point for our understanding of this problem. And we have to pause and say, at this point, we're going to switch our meaning of encoder and decoder and go back to the neural net view. So that idea of the noisy channel where you're doing Bayes' rule and decoding by taking into account these two factors, the fluency model, the language model, and the translation model, that's not what we're doing anymore. We're now encoding the input and decoding out. It's a direct model, okay? I say this without judgment. These are just sort of two ways to shape the problem. And I think if you understand the difference, you're well positioned to understand the pros and cons and understand new things. But this is much more similar to the language modeling we saw before. In fact, if you ignore the encoding of the input F, and you just think about generating this word by word as you go, it's a language model. But there's this extra thing where we take the source sentence, the French, for my running example, we encode it as in some probably vector or matrix form, and then we deterministically define distributions over the next word iteratively, one step at a time. So this is the way machine translation started working. Here's kind of the recurrent neural net version. So here we're switching from German as input, switching from French to German. You start by taking your German sequence in words, you do lookups, so you get embeddings, and then you run it through a neural network, and you get a state representation at each time step. And so that is part of your encoding of the source sentence, which is going to be a matrix. You can also run a separate neural network backwards to get a representation of each word in its right context. And so we would usually do that as well. We call this a bidirectional RNN. We're not making predictions about more words in the German sequence. We don't need to worry about any kind of prediction here. We're just encoding. This is like, I like to call these contextual word vectors. You're basically trying to get a representation of every German word informed by everything else going on in the sequence. And so you stack these together and you have an encoding of your source sequence. This is not totally different from what happens in a transformer. You're not going to think it's mind-blowing when you see what a transformer does on Monday. And then the idea was, okay, you've encoded this input. That's your context. And what you're going to do is you're just going to build a recurrent neural net that reads out the words in the target language one by one, left to right. And so, you have to have a couple of functions here. This could be like the LSTM kind of thing. It could be something else. It could be GRU. You're probably going to have some kind of softmax at the end that's going to give you a distribution over the next word. There is this one little piece where you have to decide, all right, I've got this matrix of variable length that encodes my input. How do I choose and weight the information in that matrix to decide what's relevant? that piece we'll talk about. Maybe not. It's just sort of like one piece of the puzzle. But essentially, what you've done is you've encoded the input, and now you're going to read out the output one by one using a conditional language model. And this is just a slight generalization of what we saw before in the neural language model. It just didn't have this part. It didn't have this context going in from the French or German. And so just like everything else, you could train this using the same old techniques because the whole thing is differentiable with respect to all the parameters of the neural net. And so the term they used when they introduced this approach to building machine translation systems was end-to-end. You are training your model based merely on inputs and outputs, and you plug in the data, and you don't have to think about intermediate phrases or syntax trees or components that are going to decide what phrases you pay attention to. All the messy details of those old methods that we talked about very briefly in one slide from the history of machine translation, didn't have to do it. It's just data and stochastic gradient descent and a lot of parameters and a lot of compute. And then to decode, you could do this in a super greedy way and just predict word by word. What's the most likely next word? What's the most likely next word? Turns out you can usually do better by using something called beam search. So this is the simple version of beam search in one slide. We can use this when we generate from a language model without doing translation as well. This is one of the most widely used basic algorithms in NLP nowadays. Whenever we use a language model to generate, we are probably using some variant of beam search. So I want to walk through it so that you have a sense of how it works. It's again, I think fairly intuitive. So have people seen it before, beam search? Who's heard of it? More people have heard of it. So here it is. You start out by saying, all right, there's going to be some maximum length, some bound on the length of the output. There's going to be a beam size, which is essentially how much search am I going to do. And you have your scoring function, which typically is the probability of a candidate next word, or the distribution over next words, given the words I've already generated, given some history, and the encoding of the input X, if we have it. If we don't have it, then we can do this exactly the same algorithm with just a language model, and we're generating conditioned on a prompt or a history or whatever words came before. Okay, so at each time step t, we're going to have something called the beam b sub t, which is a set of prefixes of length t. And we start off by making that just at the beginning, we have a score of 0, and it's a start symbol, which says nothing has happened yet. And we have we're going to calculate a set of finished hypotheses of length up to t that we're going to store. And at the beginning, that's empty. And we work left to right. So the time step t is going to start at 1 and proceed all the way up to the maximum length. We start off by saying, all right, here are our hypotheses of length t, and at the beginning it's empty. We copy the f from the previous round, whatever it was, and we start with an empty beam at length t. So now what we're going to consider is for every candidate we had at round t minus 1. So again, this is prefixes of length t minus 1. We consider every word we could tack onto the end exhaustively. And we consider what would be the score of adding this additional word v onto the sequence y. And we call this a hypothesis. So we put it into h. And we're exhaustive here. Every possible candidate of length t minus 1 with every word that could come next gets scored and thrown into h. And now what we're going to do is we're going to think of h as like a data structure like a heap, where we can easily, cheaply pop off the highest scoring thing. So the score of a hypothesis on h is the score of its prefix, which was already calculated earlier, and we're adding on the log probability of the next word. So this is us estimating the total probability of the sequence that we're going to generate by adding on the log probabilities of each of the words in turn. So then we consider this candidate. We take the highest scoring one. It has score s. We'll call it y. And we say, does this end in the stop symbol? If it doesn't add in the stop symbol, then add it into the beam. Throw it onto the beam. This is going to be one of our top candidates. As long as the beam doesn't yet have k things on it, we're going to keep doing this. We're just going to keep adding candidates to the beam. However, if it does end in a stop symbol, then we're going to throw it onto a finished hypothesis. Okay, so we're keeping B is going to be things that aren't done yet. F is the finished hypotheses. If at any point during this algorithm we've reached the point where we have k finished hypotheses, then we stop. And we return the highest scoring hypothesis from F. So we basically run this algorithm until we've generated k hypotheses. And what it's trying to do, and you should be able to see this through the choices that are made, is trying to find a high scoring sequence. We could do this in a very greedy way. In fact, if you follow this algorithm with beam size 1, what you're effectively doing is iteratively choosing the highest scoring word until you reach a stop symbol. Okay, it's a little more general. It's broadening the search a bit because that greedy thing might make a bad choice. It might choose a word that gives us a high probability now, but shut us off from possible longer sequences that would have a better score overall. So what we're doing by maintaining the beam is allowing multiple hypotheses to kind of compete for a while until we have k that are actually finished, and we don't stop until that point. The runtime of this algorithm will depend on the beam width. It's very fast if you have a small beam width. As you increase the beam width, it gets longer. Exactly how long, it's harder to analyze because it really depends on the probability distributions. If you let k and m be arbitrarily large, then you're basically doing brute force exhaustive search. So you can broaden this as much as you want. You will not be able to afford brute force exhaustive search for very long. Eventually, you will run out of memory and time. But beam search with finite k, finite m, it has no guarantee, like many things we use now in machine learning. And people have tried to tweak it and come up with variations and improve it. Randomness is sometimes used. Pruning, something called patience. We wrote a paper about patience. There's lots of different variations. Go if you love if this fascinates you. There's more work to be done here on decoding. I think one of the interesting underexplored areas in NLP right now is if I have more constraints or knowledge about how I want my output to look, how can I bring that into the decoding algorithm so that I can quickly get to a good answer that is computationally efficient and meets my constraints. Oh, we're going to have plenty of time for questions. Great. So the last point I want to make, and we touched on this during the Q&A earlier, is about data. So I think data and evaluation are two things that just don't get equal footing with modeling. People love to talk about models. But now that we've landed on one model, like all the things I showed you today, they've washed away. We don't use them very much. We use one model. We use the transformer. That won't last forever, I promise. But for now, the modeling is really kind of uninteresting. I mean, with all due respect to whoever's teaching transformers, you want to learn it. It's kind of cool the first time you see it. But after a while, it's like, the way we solve problems almost always is some variation of the same basic ideas. And what really affects where the field moves and whether we make progress and what kinds of things we build is what we're evaluating and what data we're using. And so I really think the skill set has shifted quite a bit. It used to be we build a new model for every problem. And we would have, when Andre was a PhD student, we would have these deep conversations about how to design models to solve different problems and how general you wanted to be. And now it's like, it's the same model. It's all the same model at some level. But the data makes a difference. So it was very early on, as soon as people started realizing how valuable data was for NLP, they realized that getting more data was better. And it was really fortunate that happened right at the time when the web was coming to life. And the web came to life in the 90s, and then it just kept growing. And so there's always more data. There's always more diverse data. One particularly exciting time was around the time this summer school started. It was like, oh, there's a social web now. Now there's tons of data of people talking every day, talk to each other, and it doesn't look like edited news pages and formally written language as had been the norm in NLP. Now there's just all kinds of language, and the diversity of languages that were represented was growing, and still continues to, I think. And we've gotten to the point where it's just easier to get very, very diverse data. We have more data than we can look at. One of the people on my team calculated how long it would take somebody to read 1 trillion words, and it was like a few hundred years without sleep, something like that. I might be off by an order of magnitude, but it was more than we have, right? So I mentioned the DOLMA paper earlier. So you can read, you can read what we wrote, how we documented the construction of our open language modeling data set, and hopefully it will make you feel optimistic about the future. But it will also make you feel overwhelmed because there are so many choices to be made about the data and so many considerations that come in, and a lot depends on what you're ultimately trying to build. I think we have to kind of point out that now that language models are not just providing a fluency score, but actually they become the engine of producing text, that it's not just an academic exercise anymore. It's text that people use. Like people who know nothing about language models are using language models to produce stuff that they are then putting into, well, in the United States, they've tried to put it into court cases and laws and possibly your medical, God knows, right? So this means that that use, that now very widespread use, and the sheer quantity of data that's going in on the training side have opened up all kinds of new questions and concerns about what does it mean to have quality data? What does it mean to build data sets that will lead to fair model behavior, respect privacy, understanding of cultural biases that could be picked up by the models and then repeated back. We've done work on this. Many people are now doing work on this. I think there's a lot more to be done to understand not how do we build the perfect data set, but how do we build a data set for the problem we want to solve that mitigates these concerns as much as possible. So that's why over on the right, I say not just increase training data, but also improve it toward the things you care about. But I want to close by drawing your attention to all the question marks on this slide. It's all the things that we know how to do on the modeling side to build better language models, increasing and improving the training data, developing better inductive biases, making the model deeper or giving it more capacity. All of these things, the link to those and the things we care about at the end, like getting applications that work better for humans and advancing our understanding of language and maybe other things, there are a lot of hops there. And so, if you take nothing else away from this talk, you should recognize that there's a lot we don't know, and it's, we're constantly evolving in our ways of drawing empirical links between the things we can control when we look at the nuts and bolts of machine learning and how it affects the world. Okay, that leaves us, I think, 12 minutes for questions. I'll share my slides with the organizers so you have all the references and can find all this stuff later. I saw several typos, and Mario pointed out that my exp in the perplexity equation should have been a 2 to the power of function. I'll fix it. Hopefully the typos didn't distract. Happy to answer whatever's on your mind.
Thanks for the talk. I have 2 questions, amongst many others, but I'll start with these 2 first. So first, I think I want to ask about the data. So like you were saying, when the web first came out, there was a huge body of work that was about using the web as corpus. And now we have these models, and there are some works that are beginning to use these models to generate data.
Yep.
And so I was wondering if that is a good way and what your take on that is, because I think when you take data from the web, it's sort of like a primary source.
Yeah.
It's humans. It's still humans who generate. Yeah.
Maybe.
Maybe. Yeah. But
yeah. I mean, this is an old concern, actually. The area when web as corpus was a big thing, the area I was working in was web as parallel corpus. And like one of my very first papers was the web as a parallel corpus. How do you find parallel text on the web? And we built the biggest English-Arabic corpus of the time, which I think was 1 million words each. And it was huge, right? And one of the worries we always had there was that we were actually scraping machine-generated, machine-translated text. And so then, what happens if you train a model on other models' output? Well, that's a whole research area now. We call that distillation. We'd like to know that that's what we're doing, right? But I think we may actually be, I hate making predictions about the future, but it may be a magical time right now where the corpora we're building for training language models have only been relatively lightly touched by language models. And in a few years, when you scrape the web to build a corpus for training a language model, you're going to have to think very carefully about where it's real text from humans and where it's not. Is it inherently awful for some of the text that goes into training a model to be automatically generated? No. I just think you should know, what you're using and have a sense of what's going on. Many people, including myself, are very excited about the potential for synthetic data. In fact, again, you're getting to know me. I'm a bit contrarian. I have sometimes argued that the only reason we build language models is to produce data for other things that we actually care about. It might be the case, right? It's probably a little extreme. I don't think synthetic data is bad. I don't think it's the worst thing in the world if some of the data, if the text was useful and it's relevant to the problem and it's fluent, I don't think it's not like tainted by the fact that it was generated by a machine. The question is, in what ways is it different from what we really want? And can we detect it? And that's a really hard problem. I don't know. I think, I would give the simple answer that we would like to know as much as we can about the data that we're using and control it in the ways that matter, but we really don't know what the effect of that will be. Okay. I think we shouldn't just blindly assume that anything we scrape is going to be great.
Sure.
Yeah.
Sure. Okay. Thank you. Yeah. That was a really good answer. Thanks. So the other question I had was, so for the first part of the lecture, you introduced the idea of perplexity. And for me, I'm struggling a bit to see the difference between perplexity and entropy and cross entropy. So could you maybe?
Yeah, it's very, very simple. I skipped this part because I assume cross entropy isn't a totally familiar concept, but maybe it's worth bringing up. So what you're doing first is you're calculating the cross entropy of your model distribution with respect to the test data. Okay. It's like the loss, right? It's basically the loss if you think of the loss that you're minimizing when you train the language model. You're calculating the loss, the cross entropy on the test data. Then you're applying an exponential function to it. That's all.
Okay, so perplexity is entropy with the exponential.
Cross entropy.
Cross entropy with the exponential.
It's bits per word raised to the power 2.
Okay. Okay.
Yeah. Or 2 raised to the power of bits per word.
Okay. Cool. Yeah, that's great. Thank you.
So you say perhaps these models can improve our knowledge about language, but as you said, a lot of the models are built kind of while discarding what we know about language or knowing that that's not really how language works. So I'm wondering if you can say a bit more about how exactly they can advance knowledge. Do you think maybe they have some insight into, I don't know, whether or not Chomsky is right or wrong, or how exactly does that work?
I'm not going to touch that Chomsky thing. I met him once. He's a very interesting person. Let's see. I think, let me give you kind of an idealistic answer, and then I'll give you the more grounded answer. The idealistic answer is think about Copernicus. If you have a better model, if we aspire to building better models, and we show that they make better predictions, then we should be moving in the right direction in terms of understanding the things we're trying to predict. Is that universally true? No, probably not. Do modern models of climate give us a better understanding of how climate works? I think that might be. I don't know that area, but I suspect that's a stretch. But in many areas of science, a big part of making progress is you have a model. But when we all learned chemistry, we learned a model. We didn't actually, when we learned physics, we learned models that were wrong, but we learned them first, and they slowly moved us towards a more advanced understanding until we stopped taking physics classes. So that's the kind of thing we should aspire to. And I think it's been pointed out that every other way we evaluate NLP systems is divorced from making predictions about real things in the world. Like this is something that like kind of deeply troubles me. Every time we do an evaluation on like human judgments, human annotations, human translation reference output, it's always sort of like you have to hedge against the quality of what the humans did. And humans are like, in some sense, it's a human phenomenon that we're studying, but are humans really the best arbiters of this? And we're very limited by the things humans can have intuitions about. I got really excited for a while about using NLP systems to make quantitative predictions about the world, like how will people vote, or what will happen on the stock market from text. I wasn't interested, I wasn't trying to profit off of this. It was more just, is there information in this text that is predictive of this other thing that's not text? Perplexity is the same version of that. It's just predicting the text. It's fit. Anyway, so one of my friends once made the point that perplexity is like the only thing we have in NLP that's really like science, because it's making predictions about the future. Have we gotten advances in linguistics out of that? I don't know. I will say that the idea of surprisal does get used in some areas of the cognitive study of language. Like they take the conditional probability and they call it surprisal. They do some transformations, and it's like this useful quantity that's predictive of some things and sort of suggests something. But I think there's not a tight connection, and I don't want to claim that large language models are the future of linguistics. I'm not saying that. I really am not going to go there. I think there's still a big gap between what these things can do and understanding how they might be used for the study of language. But I will say all of my friends who do linguistics are very interested to see what happens with these models and think about how they might be used and whether they have value in scientific settings over there. And I think it's good to keep that dialogue open.
Up here, hey,
Hi.
thank you very much for sharing your thoughts with us. I'm not gonna ask a question about transformers, but what's your take on like the newest advances of like recurrent architectures like state space models, Mamba, RWKV, or maybe even XLSTMs?
Yeah, I mean, you know, it's like the longer you're in the field, the less surprised you are when old ideas come back. Right. That's why I still teach RNNs a little bit, right? I think you are now prepared to go read those papers in a way that if you hadn't seen RNNs before, you were not. I think, you know, the challenge is how do you take the hardware you have today and the data that we have today and make things that can compete and improve over the transformer, ideally are cheaper and perform as well. I mean, I'm thrilled that people are continuing to try and make progress on architectures. They have my strongest encouragement to keep going. The particular, I stopped having opinions about the specifics of models or feelings about the models a long time ago because I have no intuitions about them at all, right? They're equations. You can't look at these things. If you look at these things and they give you strong, passionate feelings of this is correct or this is incorrect, you need to get professional help. These things are really divorced from the data. It's an empirical question. We have to see, can they be made to work? If you love the transformer, you should ask yourself, why? What is it? Is there actually an intuition that you have from that? Is that useful? Can you put it to work? Or is it just, this is the first thing? We all have an attachment to the first things we learn, right? So I am completely neutral on whether these are a better answer or the right answer. It's an entirely empirical question. The main things I'm hoping for in the remainder of my career are that the models will not be so expensive. I would like them to be cheaper. I would love it if they were more interpretable. Like we could gain intuitions about them and run experiments and then have insights about how to improve them further to make things work better. I don't know if those new models are going to give us that, but I think it's great that people are exploring. And I really hope that we're not stuck because the hardware is now being developed for the transformer. Transformer was developed for the hardware. And now they're in this like, you know, maybe we're in some kind of locked position. That would be bad.
Cool, thanks.
Hi, thank you for the talk, first of all. With respect to this sort of shift that we're starting to see from getting all the data to maybe getting good quality data, I was just wondering, what's your opinion on the best way to mitigate this dilemma that we're having? Because like you mentioned, it's fully impossible to do any sort of manual human checking of the data at this point with the amount that we need to use. So yeah, I just wanted to hear your thoughts on how to mitigate this
Yeah,
problem.
so I would mention a couple things. I don't know, one sort of practical thing that seems pretty clear now is that deduplication seems to be good. So if we have, and I don't think that's a completely solved problem, but the less repetition you have in your data, another way to say it is the more diversity you have in your data up to for some notion of diversity, it's probably a good thing. And so that works against, you know, repeated occurrences of the same tropes or stereotypes or whatever stuff you don't want. If you have less repetition, the effects of these things will should diminish. I'm being hand wavy, but that's the intuition. The other thing that I think doesn't get talked about much is processes for understanding the data. It's not like we can't do anything, right? We can't look at all the data. That doesn't mean we're completely helpless. So tools that let us explore and understand what's in our data can be quite useful. We had a paper about a year ago called "What's in My Big Data," and it's like really, really, really simple tools for exploring your data set. Like, what are the most common n-grams? It turns out, you know, we made very simple discoveries, like the amount of chess game transcripts that are in standard language modeling data sets is astronomically larger than I would have thought. No wonder they're good at chess. They've memorized all the games. Maybe, okay? So I feel like you can get a sense of what's in your data without looking at every last page. And we have tools from information retrieval, from machine learning. People used to work on topic models. There are all kinds of things that we could be doing and that could be, we could develop better processes for getting a sense of what's in there. One thing that I am working on now with students is, now that we've released a model alongside its pre-training data, is how do we link back what the model says in giving an answer to a question to the pre-training data? Some people call this attribution. It doesn't have to be for attribution purposes. It can also just be to understand, why did the model get this question right and that one wrong? Or why did it get this one right at this point in training and then get it wrong a little bit later, or vice versa, right? Can you trace things back? This is we don't know how to do it yet, but it's a great thing to find ways to probe into your data and understand what's there, either guided by a particular thing you were trying to do or just in general. I think it's a great research area.
Thank you so much.
Hi. So maybe a question on this idea of machine translation. And okay, it might be difficult. We don't have perfect examples, perfect data. Sometimes can be difficult to evaluate if the answer was the right one or not. But for example, can we try with things that could be controllable? Like we have still with this idea of deciphering or encryption, like we could generate, we have some set of data, we have some kind of algorithm that transforms it, and we could like imagine using a transformer to decrypt an RSA. Maybe that's not really possible, but like this idea we can generate we have some sort of text, we have a function to translate into some random words, and then we could probably try to, because then we would know when it's correct or wrong, if we could kind of try to find a model in this way.
Yeah, I think what you're proposing is to basically contrive some kind of evaluation with synthesized data that would let you test kind of some capabilities of the model and see, could it learn to do this? Could it
Could
learn
it
to do
learn
that?
the original function or an approximation to it?
Yeah.
And if somehow that will tell us
So this is
architecture and stuff.
this is a kind of work that my advice on this, whenever I hear this idea of like, oh, maybe we could contrive something that would let us, I think it's fine if you know exactly what you're trying to test. As an exploratory technique, this will just drive you crazy. Because you can come up with all kinds of ways to transform data and all kinds of functions. And you can then go run an experiment and it will work or it won't. And then it'll lead to some other way to transform the data. And you'll go in this circle and you will not discover anything new that's relevant to building translation systems for actual natural human languages. So my strong advice, this is what I say to my students, your main experiments in your paper should be on real data and real problems, as close as you can get to those. And if you want to do synthetic experiments to test the boundary cases, you have to know exactly what it is before you start trying, or I will never be able to pull you out of that rabbit hole. You will spin around on this forever, especially people who are mathematically inclined. It's a real risk. You have to know exactly what will the answer, what are the possible answers I could get, and how will I act if I get those answers. I will not let my students run these kinds of experiments without having perfect clarity about empirically how they will take action given what they see.
Thanks.
It's dangerous. Synthetic data is dangerous.